Good morning. Let me begin by thanking the organizers of the Science Day program at RRI for including me in that program. And also I feel honored to be in the role that I am, and I think I'm looking forward to this stint I will have as the director of Randomness Institute. I'm a cosmologist, and so my broad thing would be gravitation and cosmology, and I would like to narrate stories to young people to tell you what we have achieved in the last century. And in that sense, although I work on that on a daily basis, so sometimes you get kind of slightly immune to the excitement, but nevertheless, whenever I'm sitting on my own during a weekend, it never ceases to amaze me how much we have understood about our universe, and particularly in the last 3-4 decades. And I would like to convey that excitement to you. Okay, so let me begin with this picture here. This sort of shows you the splendor of the skies. I mean, this is why human beings right from the beginning have always wondered, where are we, what are these, and what's our place in the universe. It has been a quest as old as humanity. And this picture is by a very well-known astrophotographer, but actually he's a practicing astronomer at the Indian Institute of Astrophysics in charge of the Hamday facility, the J.M. Joke. So let me show you another nice picture, and where you see the Milky Way reflected in a lake. And these are the things that any kid anywhere in the world, although most kids now in urban areas unfortunately don't get to see this. I understand you can see it in Gauribindu to some extent, so I'd encourage all of you to go and visit it. But it's splendid. I mean, for people who have seen it, this is really amazing. Now these are stars, and we understand these are very local. These are in our own galaxy. What used to be called an island universe, because we didn't know there were islands farther away. But let's look away from the belt in which most of our stars of the galaxy are, into a faraway region. I couldn't get far away, but you look at a region where you don't see anything obvious, and then look at it through the best telescopes you have. And this is what is called the Hubble Ultra Deep Field. Okay, so Hubble telescope, as most of you would know, is one of the most capable space telescopes, and it peered at one region of the sky for a long period. And what you see here is galaxies all the way to as far as we can look. Okay, there are galaxies at very large distances, redshifts as we call it, and so much so that light that is coming to us is from a time when the galaxy was just barely forming. So some of the splotches that you see are actual galaxies, but they look very ill-defined, is because they're just forming. Right? They're not like nearby galaxies which have nice spiral structures and all that. Okay, so we are immersed in a universe which is vast, full of galaxies. Okay, so I don't know how many of you, maybe all of you are too young to know about Space Odyssey or the book. And there, this guy peeks into a wormhole and says, "Oh my God, this is full of stars." So, our universe is like that. When we have learned to peer around, it's full of galaxies. And if I were to take a tour through the universe, and this is a movie borrowed from the site of European Space Southern Observatory, you can see, if you do a flyby, there are galaxies, and galaxies are kind of organized on a very interesting network. It's not regular lattice of galaxies, neither is it totally random, what you would say, there's no pattern to it. It's a very interesting pattern. So for many of you who are in condensed matter, soft condensed matter, this, you see it on your Petri dishes and little systems. And these would be very complex phenomena, right? So I am always of the opinion, although I'm not a great historian of science, not at all in fact. So I used to wonder that suppose we were to start cosmology today, not 100 years back, okay, actually I think we would not have had the success we had, because we would have been confounded by the complexity first, and maybe struggled a lot more. So we did not, and we now are in a position where where we know the entire history of the universe in a very robust as well as reliable fashion, in a quantitative fashion. What I mean by reliable is, we can give you numbers, but within a framework. And I would like to tell you in my talk here what the current framework we have for understanding the universe, what remains to be understood, and sort of try to convince you that that's been immense progress. Okay, this model that we had was one of the earliest models. When we learned that gravitation could be applied to the scales of the universe in a reliable way. Newtonian gravity could not, right? So then we got into this thing where, this 10 to the minus 32 seconds, I leave it at that, but anything from here to here is based on lab tested physics. Okay, that's amazing. The universe seems to obey the same physical laws that we see on the ground here, right, in your labs, in LHC. And then depending on how much you believe what we know about the earlier history and highest energies of physical interactions, you can push yourself back. So some people would say, oh, we know everything up to here, someone will say here. But broadly, there's an immense 14 billion years minus some 10 to the minus 32 seconds or 10 to the 16 seconds that we may have some speculative ideas. Rest of it is physics that many of you here work on. There are experts in our institute who know many aspects of it. So what really allowed us to do cosmology is with the modern observations, but this is already 1970, not modern at all, Lake Observatory Survey, where we did not really look at the entire network of galaxies. We didn't have the ability to do so. But we could map the galaxies as they are on the sky, right? And that's the easiest thing to do. You don't have to find the distance to the galaxy to make the 3D thing. And what really leaps out approximately is that no area of the sky looks to be specially endowed with galaxies or devoid of galaxies. Now, of course, you would see kind of patchy pattern, but remember we are in the 1970s and we are looking at a broad picture. So people with glasses like me and bad enough eyes, just take off your glasses and look at it. It looks like a very white patch here and a white patch here. It's not the full sky because in those days we couldn't peer through the galactic plane as well as we can do now. Okay, but this is a amazing picture to me. This is features in people's textbook. And I always look at it and say, look, this is what told you that there are simplifying assumptions we can make of the universe. And what's the major simplifying assumption? That at least to the extent that we can make out, in any solid angle that you look or any direction that you look, the distribution of galaxies is on the average the same. You go project it all back, there's nothing special about one part versus the other. And then you have to do something which we do in science, which is have a basic principle, like they have fancy names, but the idea that we are as human beings do not occupy a special place in the universe. This we learned the hard way with Copernican revolution, that we were not at the center of the universe. We are revolving around a very mediocre star in a mediocre galaxy. Later we realized it was a star in a. But you now say that our galaxy is nothing special. So if this is what we see, roughly this is what anyone in any distant galaxy would see around there. And then it's mathematics. If you have a medium which is isotropic at all points, it is homogeneous. It's a mathematical theorem. It doesn't go the other way. For young people, I would encourage you to think of counter examples the other way. So many logical statements go one way, and often people narrate it the opposite way, and even in science or administration everywhere. So that you should be very careful about. This basic thing is isotropy around every point implies homogeneity. And this is encapsulated, as I said, in something grand called the cosmological principle. And this was propounded, a century back, right? So there was in the early 1900s, it was already, something that was used to build models based on this, at that time, very new theory of gravitation given by Einstein. And people came out with a big surprise that if you did that, you had to contend with an expanding universe. Okay, so smooth expanding cosmos. It could be also smooth contracting cosmos, but there were observations which indicated that we were in that branch where it was expanding, or branch of solutions. So the basic framework of cosmology is very simple. There is a three-dimensional space-time, a spatial surface at any time, and that spatial surface can be thought of like a fabric or a magical kind of membrane that can expand, and essentially space expands. So things even embedded in space at the same location in space, their physical distance keeps changing. And when we see the universe expanding, it is that picture that you should carry in mind. And then it has an expansion history which tells you how much expansion happened at what time. And in the early days, we knew there was a whole family of solutions to this. And we also realized something very interesting, that the equations are so simple that it's an algebraic equation. If you tell me the current content of the universe and its nature, then I can tell, and also the expansion rate now, you can figure out what the universe did in the past and would do in the future. It's very deterministic within this framework. But we didn't know these numbers. When I started cosmology, these numbers were very poorly known. The expansion rate itself, which is called the Hubble constant, was known to a factor of 2. People fought to death over it. And but now, what is interesting, I don't have that, but we know which solution we rely on with fairly high confidence. That's because we figured all this out here. This equation doesn't give you room for anything else. Okay, so just to recap, so Einstein's relativity, which is the Einstein's gravitation, theory of gravitation, applied to uniform distribution of matter, which is what the cosmological principle says, leads naturally to an expanding universe. There's no, we are not doing any trick here. That's one of the solutions. It could be also contracting, as I said, but that's a time reversal kind of thing, but you don't really see that now. I wanted to emphasize that often expanding universe is depicted, or not necessarily meant to be depicted that way, but in BBC serials and all, when they talk about Big Bang, you hear a roar and gas going out. To me, for any kid, if I was a kid, I would imagine an explosion happening. This is not an explosion. Okay, it is basically this quaint phenomena that theory of gravitation allows, because theory of gravitation that Einstein propounded made space-time dynamical. And if I look at it like spatial three-dimensional surfaces evolving in time, then you would find that this spatial hypersurface at different times, the galaxies just seem to be moving apart from each other. And it doesn't depend on where you are. To this galaxy, everyone else is running away. This galaxy, everyone else is running away. And there are a lot of phenomena. I'm teaching a cosmology course now to ISER kids, and the first half was just to get this through. This is all that is different in cosmology. Rest of it is basic physics applied to the expanding arena. And it has these interesting effects. Like if you see the shell of light, you can almost visually see that it seems to be struggling to get far. And in fact, you can have expansion rates so high that this light shell would freeze. It can't reach some galaxies. everything is possible, right? So let me tell you what is relevant for the thing that I will cover here. There are two things to keep in mind. Now imagine I mark out a hypothetical volume in the universe, in this distribution of galaxies. Something is ringing, right? No. There's a feedback.
It's perhaps the stage microphone.
No, it's off. This volume, if I were to look at this volume back in time, we are in an expanding universe, so there are a number of galaxies in this volume. There is no reason, broadly, for lots of galaxies to emerge or disappear. So you will have the same number of volume going back, number of galaxies in the volume in the time going back. So when the universe was half its size in terms of relative scale factor, we would have 8 times the number density and 8 times the energy density using E equal to mc square. 1/4, it's 64. The crucial thing is, what about cosmic radiation background, which is kind of there everywhere. There, the phenomena is a bit different. Okay, as you go back in time, number of photons are the same. Photon density, photons in this volume are the same. Photon density will grow exactly like the galaxy density going back in time. But each photon, because it's an adiabatic expansion, the wavelength halves, which means frequency doubles. The energy associated with frequency, each photon, doubles. So instead of a number density goes up by a factor of 8, but you see energy density is going by a factor of 16. Going back, 64, but 64, 128. So you see that radiation going back in time is getting growing in energy density much faster than matter density. While technically matter density, when I use the word matter, I'm talking about non-relativistic stuff, and when I'm talking radiation, I'm talking about relativistic stuff. But that's really relevant only for the experts in the audience and the students. Okay? So you go back, what does it tell you? That there must be an epoch when the universe, the scale factor was large enough that the universe was totally radiation dominated. At this point, we know what the radiation content of the universe is, as I'll get to. And given that, we know that about when the universe was about 10,000 times smaller, all these scales. For all time before that, the radiation density dominated the universe. So you're in a very, very interesting situation. That early universe is very easy. I told you there's this model and you need to know what dominates the energy density at that time. And it's largely, it's almost radiation dominated. Not almost, it is radiation dominated. In the early universe is radiation dominated. Well, the question is, that tells you that the radiation path in the universe is extremely important, right? Because most of the history of the universe, if you compute, was radiation dominated in cosmic time. Okay? And where is this radiation? And that was an amazing breakthrough. So in 1965, very serendipitously, there was a telescope being set up in Bell Labs, which detected an excess noise which they couldn't understand. And finally, after doing everything that radio astronomers do to clean up the noise, someone told them, hey, but there is this bunch of people very close by in Princeton who seem to be looking for a cosmological signal, which is essentially going to be a noise, right, excess noise. And then they talked to each other, and rest is history. Penzias and Wilson discovered the cosmic microwave background, and if this cosmic part came because of Princeton, I should also say that it was amazingly nice of the Princeton group, particularly the senior leader there, not to force himself on the paper, but the interpretation of cosmic was largely because of the cosmology team, right? And the statement he made is, guys, we have been scooped. So he accepted that they had seen this path that they were looking for. And what you had discovered is the dominant radiation content of the universe. 99% of the radiation content of the universe is accounted for in this path. Okay, it's an extremely isotropic path which sort of lends a huge support to the isotropy that we are talking about in terms of galaxy distribution. So there you don't have to take off your glasses. I mean, none of you are capable of detecting differences at the level of 10 to the minus 5 if I give you this map of the CME sky in kelvins. No. And this thing is glowing, has a black body which has immense implications, and has a temperature which is very well measured now to the third decimal point. Okay, and this is the clinching support for hot Big Bang model. Okay. Okay, so let's see what has happened. So when we look out in the sky, as you look further away, when you're seeing a distant galaxy, you're looking at it in the past. So you should realize that naturally, because things cannot travel faster than light, we are in a time machine. As we peer further down in distance, further out in distance, we are also looking back in time. Technically we are looking back on a light road. And so, if for any observer in the universe, when they look back, they will see galaxies and stuff here, and then nothing for a period, and then a plasma screen which is glowing. Okay, if you go and put a thermometer there, you would find that the plasma screen is at a temperature of about 3300 Kelvin. It's very hot plasma. Not very hot, but hot plasma. But then, because of the expansion of the universe, what you see here are photons with that distribution at a temperature of 3000. So 3300 divided by 3, is 1100. The universe here is 1100 times, smaller in scale factor. Everything is physically 1100 times smaller on this surface. But it's amazing. Nature has a transparent window to a time when the universe was only 500,000 years old. And remember, the current age is 14 billion years. Okay. And for people outside this audience, we use these giga years and giga and all this. These are basically short forms of billion and stuff like that. And the universe in this window is totally transparent, except for things, details, but largely that's true. And the universe beyond that is a totally opaque wall. It's like we hit a fog wall as we look out in the universe, and it surrounds every observer. Now you might think, is there physically a thing all around us like a shell? It's not a shell in time, in space. It's a shell in space-time. Okay, so it is a shell in space, but we see it all around us because it is coming from an epoch back in time. If you look at this light cone, this conformal time and co-moving space, and you would see that there's a radius. So when you go back to the hypersurface, which is 1100 times smaller, when the universe is 500,000 years old, this is 14 billion years old. You can't peer with electromagnetic probes beyond this surface, because beyond that the thing is a plasma, and plasma scatters light so much that you don't get coherent information. See, one thing you should realize is when you say you can't see in the fog, it's not as if nothing is happening or there's no information beyond it. There is information, but the information is so scrambled that you only see the photosphere. Like on the surface of the sun, what we see is the photosphere, right? And so there is this whole history of the universe beyond that hidden here. But this, in terms of distance, is only the last 3% of as far as you can look in the universe. So this probe, for example, in particular, is probing the volume of observable volume of the universe to as far as you can really look. Only the last 3%. But last 3% is very exciting. Why is that? Because not only is this path isotropic, very isotropic, but I told you it's only at the level of 10 parts per million. Okay? It has also revealed signatures of little fluctuations. in the temperature of the microwave background. And this happened in 1992, and that explains for you the structure we see in the distribution of galaxies. We see very well correlated structures. These again technically are random, but they are correlated random fields, right? And that is kind of very important in what we deduce. And in any typical volume of the universe, it's full of galaxies, and this is from a real data of a 2-degree field. I forgot to refer to it here. It's now relatively old, but what you see are these galaxies with their colors reflected, and this milky thing was put just to guide your eye to see that there is a rich cellular structure. Okay, but you should also realize that around each of these galaxies or all, there's a dark matter distribution which doesn't look exactly like this, but it's good for our first thought. Okay, now what do we have? We have this plasma screen where what is being played out is the universe when it was 500,000 years old. Okay, and what is being played out is essentially the origin of structures. We know that there is some high energy physics phenomena which very magically is actually quantum for people in the LAMP group probably. So we believe that that phenomena is what created these perturbations, which we can't see here, but we can see at this end of the plasma. And this is carrying information of this and also the entire history of the universe here, because photons propagate through this history. So it's an amazing screen where we believe that what we see as fluctuations at the level of 10 parts per million have grown to fluctuations of order unity or more to form this rich structure that we see here. But that is one part of the story which we have unraveled to understand our universe very well. But for the next generation, the challenge is to connect this, right? What was the origin of structures? Okay, so let me go over it again. 3 Kelvin temperature. The temperature fluctuation is at 70 microkelvin. Okay, and I will only, there's also a polarization pattern which I will only get to briefly later, but not get into details. What is being played out is amazing. It's very basic physics. So if you look at the plasma screen, there is something which has excited it, right? Just like a lake which is being excited by some phenomena, like something happens at the bottom of the lake and you see ripples at the top of the lake. You can't see what is happening at the bottom, right? But we can, as physicists, analyze it with tools that not too many areas of science have. We can go and look at it as a more technically green function, but we can decompose the fluctuations into as if they were delta, they are localized spike fluctuations that I'm putting on the plasma. Now this is not only physics. If you have been at any music concert, Hindustani or Carnatic, you would see the percussionist actually tune the tabla or mridangam or whatever. And what do? You would see they have a hammer and they hit it. Okay, that is essentially what you call Green's function. So they are looking at the response to a impulse. Okay, that in engineering is impulse and the response function. Through physics, it's the Green function. And let's do that. So in this plasma, at some point, we create a spike of all the densities that are there, and ask what will happen. Now, what is the universe consisting of? It has baryons we are made of. We know it's at about 4%, right? We know it very precisely, but then we have cold dark matter which does not interact with electromagnetism, which accounts for up to 25%. And then rest of it is some weird thing we will talk about later. Okay, that's dark energy, right? So anything we don't know, we call it dark, and that's it. But what you see here is amazing, that you have this ripple which goes out in the baryons, which are tightly coupled to the radiation. Baryons are ordinary atoms, so they are ionized atoms, and so through the electron they are tightly coupled to the radiation path. and they behave like elastic fluid, and they are the ones which show this ripple, only the baryonic fraction. And this ripple goes out to a particular distance, and you can see that when the color changes from red to green, it freezes. That's when the universe turns from ionized to neutral. That's the edge of this plasma screen. And essentially, this phenomena cannot happen because the atoms have lost their coupling to the radiation, so it's not an elastic system at all. There's no perturbation at all. So it freezes to a particular size. We know how to calculate that size. It's just the sound horizon in this very simple universe. Okay, and it is 150 megaparsec, and it's a characteristic scale which is imprinted on the CMB sky. Okay, we know the physics very well. I'm just to convince you that all this is very basic physics applied to an expanding universe, and there's very little ambiguity in this. I mean, there is also very little space to do anything more. And this is worked out. We understand every bit of what you would see if I Fourier transform this and look at its spectrum. But the question is, how well can we map it? So Kobe saw it with really bad glasses, right? So you could make out that there were fluctuations, but you could resolve a few 10 degree kind of resolution. Then in the next decade came Wilkinson microwave anisotropy probe, and Wilkinson microwave anisotropy probe saw the same thing, but at a much better angular resolution. And then the next decade, there was Planck, and this is from NASA, this is from ESA, the European Space Agency, and it has the best measurements till date. It has mapped out intensity fluctuations to the level that you can get. I mean, there's really, for most of the measurements they have given out, you can't expect to improve any further. And I should also mention that while people talk about the history of cosmological background observations in terms of these three eras, there were lots of ground-based observatories, like we have, which did phenomenal work. First polarization pattern was detected by DAISY, which is a radio interferometer, just like many of you see in your in the context here. And then there are really wonderful experiments which are now running, and there will be a next generation stuff happening there. So let me briefly mention what did we see in Planck. So the Planck gave out a map. This is the full sky. I mean, again for the audience beyond, mapped onto this oval. This is what astronomers do. And on that sky, you have mapped out what you are seeing as intensity fluctuation on this plasma screen. This plasma screen is mapped onto this. You see hotter spots in red and colder regions in blue. The range of fluctuations here is 300 microkelvins to plus minus 300 microkelvins. RMS is typically about 70 microkelvin of this. Okay, and see, this Planck allowed for the first time for us to see this screen, this map, without the galaxy masking any part of it. Okay, fairly reliably. And if you take those ripples, see what is happening is I broke up the perturbations earlier in terms of impulses and the response to impulses. These are equivalent pictures. I can do Fourier transform and also do that. If I do a Fourier transform, this is the Fourier spectrum of the sky map. And Planck, Kobe just measured this part. WMAP did up to here, right? Maybe here, there. I mean, I don't want to fight over it. I mean, but we were part of Planck, and you can see that we can see this Fourier domain resonant feature going up to the 8th peak. Okay, you can resolve up to 8 peaks here. And these peaks are essentially acoustic peaks, phenomena that you will see in a resonance tube. Okay, if you have a resonance tube experiment, you know that there's standing waves, and then there are harmonics. So this is the first harmonics, this is the second harmonic, third harmonic, going on like that, right? So it's amazing. And so then now you start questioning, is this phenomena really happening? Or is it because we had this data and we were fitting it to this kind of models? This red one is the expected prediction within the isotopic and homogeneous universe models that I told you. Given all the parameters, you vary them, but there's one that fits. And then, essentially, you might ask the question, what if we are missing something because we already have limited the kind of curves that we are fitting to the data? So we did a totally non-parametric analysis and showed the following. I mean, there were other things shown, but one thing we showed this harmonic pattern, right? This is peak number 1 versus peak I versus ith peak versus location of the jth peak, and you can see it, lines up like you would expect a spectrum from an X-ray spectrum of crystal. Okay, so even if people did not know anything about the isotopic and homogeneous universe and all the physics, any smart scientist, given this data, would see that there is something interesting. There is some kind of a resonant phenomena involved here. And given the information we have in Planck, we know what the universe consists of and its expansion rate to extraordinary accuracies. Okay, this is where we are really, shoulder to shoulder with particle physics. And interestingly, just like there's a particle data group list of particle masses, nowadays they have also, similar thing for cosmological parameters. Although we are not at that same level in terms of, I would say, accuracy, but precision-wise we are there. It's 1% in baryon density, 2% in cold dark matter density, and this is the best measured parameter, which is the size of that ring, right? Angular size of that ring. We know the physical size is 150 megaparsec, but the angular size, its substance is one of the best measured parameters. And then we know certain things about the primordial fluctuations and the rate of expansion of the universe. And this all can be fit within a very simple variant of this model that we were talking about. And that's why we started calling, people have started calling it the standard cosmological model. It's a 6-parameter model which fits everything that we see till now. Okay? At least definitely Planck. And the person who was one of the architects of that was awarded the Nobel Prize. I mean, this is my guess. I don't know whether how the Nobel Committee thought about it, but he was someone who could have got it anywhere in the earlier decades, Jim Peebles. But I feel that once Planck brought out these things with such robustness, he was the person who was one of the chief. I mean, it's not the only person working on it, but he actually propounded some of the key ideas. And he's one of the ones who is the most uneasy about the cosmology, fact of saying that, oh, this is cosmology and that's it, we know everything about the universe. He says it's very uneasy because, it's a simple model. It seems to work, that's a great surprise, but it need not have worked. So it's a simple model, but yet an exotic universe. Because we are forced to admit that 95% of the energy density of the universe is in some exotic form. We haven't seen it in the lab yet. Okay? Part of it is cold dark matter. We cannot see it directly, but we only infer its existence through gravitational interactions. Then there is something weird, which is dark energy. I am of the camp where at this point till proved otherwise, I would say it's a new constant, fundamental constant called the cosmological constant, which behaves like a dark, smooth form of energy, which reacts repulsively in the in a Newtonian picture against under gravity. But most importantly, these are all important areas to probe. But what I'll go forward with is the fact that all these inferences have been made, assuming there was this hammer which was at that other side of the plasma screen, creating these perturbations, which tells you that there is ultra high energy physics, possibly of a fundamental nature, that we don't understand because we don't have the mechanism. We have a broad range of a broad paradigm under which these mechanisms work, but we don't have the mechanism. But the rest of it, all the deductions of those numbers are very, very robustly done. Okay? So the paradigm of CMB fluctuations, acoustic phenomena, this has been made by other things other than the plot I showed you earlier with this non-parametric thing. The most definitive thing is this ring being seen in the polarization pattern. So this is Planck data, and if you stack up the polarization around hot spots, hot intensity spots, the polarization has a particular pattern. Polarization actually maps the velocity field, and you will clearly see the ring, right? And this is what you would have, this is a simulation. So it's as good as simulation, and this is something that will go into textbooks. I mean, this is an amazing confirmation of something that was called Sakharov oscillations. Then, Peebles and Liu talked about it, and there were, great people talking about it. Similarly, this is hot spots. You can line up the cold spots, and you see that the velocity pattern has reversed itself, where whatever was red in the velocity is blue. I mean, this tells you the radial direction. The thing has reversed. What was red is blue, what is blue is red. If you have questions, I can get into this a little more. This is to do with the polarization. Then, I also told you that we believe these tiny fluctuations that I am seeing at this plasma screen are what grew to the large scale structure. And then, how well do we know that? We have this picture that this CMB map is the blueprint from which these grew. And if this is correct, then of course we are in a great place in physics. We know the initial condition and the final state, initial state, final state. We know a mechanism, and it has some dials. And you dial it right so that it matches. That is what we have done, right? So we know these parameters so well because we have a consistent picture going from here to there. But you have to ask, is this correct? Is the mechanism really the one? And that we have confirmed through something called baryon acoustic oscillations. If you look at distribution of galaxies and look at the correlation function, normally it just falls off with distance, but there's a tiny bump corresponding to the same ripple that I was talking about, because baryons got dragged with it. Okay. Similarly, since there is intervening large scale structure which is growing in a particular fashion, it distorts the bundle of CMB light that is coming, it shears it, and we measure it as something called CMB weak lensing. And those measurements have gone very well. I won't really get into it. It's a very subtle effect. Only Planck could see it. You can see this is the difference it makes if you have the lensing effect or not, don't have the lensing effect. Nevertheless, Planck could detect it and could make a map of the integrated mass density along line of sight. It's a very preliminary map. This is where we can improve a huge lot with future things. But nevertheless, we have just started. It's like the Kobe map for CMB fluctuations. So we are broadly in a situation where we understand cosmology in this part of the drawing, where there's a homogeneous and isotropic patch of the universe. And given those conditions, we know how the universe would have evolved. But it could have evolved from something really exotic. We won't know till we probe further. And there's a huge discovery space. Okay, and how are we doing with time? Few more minutes. Okay, great. So then let me sketch out one particular direction of many directions you can look at. You can look at cosmic topology, you can look at all kinds of things here, because all of them may leave a subtle effect. You must have seen papers of multiverses colliding with each other. Rather unlikely. But we have to take steps towards observing the early universe. This step between what created the perturbations and the perturbations we see in the microbackground. So this is the picture. So this is the cosmic screen, and we have understood everything we did from translating this picture to this picture, connecting these two pictures. But we need to still do this. We have a fairly good idea or paradigm within which to work. There is a concept of inflation, which is necessary for various reasons. To have something, you may not call it inflation, but whatever you call it, it has to do a certain number of things. And associated with that will be quantum fluctuations that you can very reliably calculate with quantum field theory on curved spacetime. Those results are as robust as your belief that there is Hawking radiation. Okay? With that, your picture would be complete. But how far have we gone there? So inflation paradigm, naturally gives you a homogeneous isotropic patch of the universe, large enough patch, where our cosmological arena can be played out. Okay, that's the cosmological principle. It's consistent. It also predicts for you that the geometry of the universe is, flat. The geometry or spatial geometry of the three-dimensional surfaces is Euclidean. We have got that. Now we have also confirmed that there are perturbations because we see them in the microwave background fluctuations. They are of a nature which is naturally emerges out of generic models of inflation. They, of course, the density perturbations are what we have seen. They are of a nature with no entropy fluctuation associated. We know that very well, up to 5% possibility. Like, if there are non-adiabatic fluctuation, entropy violating fluctuations, then they have to be less than 5%. And the underlying statistics is Gaussian. The only major thing that will really, say that we are right and little a fairy tale come true is to see the gravitational waves from this early phase. Because just like density perturbations are created, the same physics generates for you. It's exactly the same physics. You can't avoid having a gravitational wave background. The question is that what is the level of that? And model to model that will vary. So we parameterize it very simply with the ratio of gravitational wave to density perturbation amplitudes, right? And that is given by a number called R, just R, or whatever it is. This connects to the energy scale at which the physics that was has caused inflation or had caused inflation would be related. And currently, our bounds conservatively is 0.07, but actually 0.03 or something. We are really pushing very hard on that boundary. But we have not seen anything except for a false alarm that we had from myself. And it's a 2-2 and must-do for cosmology. And a big community of us think that it has to be done with another space on mission. Okay? Because there are limitations to pursuing it from ground. US has a huge program to do that. But there were many proposals which are still awaiting thing. One of them which has gone forward to some extent is the Lightbird proposal of Japanese guys who will work with ESA and NASA to do that. And we will see, but they have in the low resolution band, so it's a bit less satisfactory. So in 2018, Cosmology Consortium called CB Bharat here, it was set up largely driven by this goal to propose to ISRO absolutely do it all kind of a mission. We will map out the CMB sky such that we won't have much more in terms of the fluctuations to worry about. There will be more in terms of the spectral nature, but it will make the first steps in the spectral science also. I won't go over the details here, but it's a very comprehensive, so near ultimate polarization survey. The ultra high goal or scientific promise, that is the big carrot, is that we may see this primordial gravitational wave background. If we don't see it, it spells very serious trouble for the paradigm, because we'll have to switch to another class within it. Okay? It is gravitational waves of quantum nature. Remember, LIGO detected gravitational waves, but they are classical. These gravitational waves are generated by quantum fluctuations. We know that. So it's kind of a Nobel Prize kind of goal. Okay, and if you were to listen carefully at the Nobel lectures of Rainer Weiss and Kip Thorne, when they received the Nobel Prize, you will see both of them mention the next big thing they would look forward to is this. Right? We see the primordial gravitational waves. And then in doing so, we have to have a satellite which will do a lot more. In neutrino physics, map all the dark matter. That map I showed you now from Planck is like the early days. You can just get maps which are much finer than that, and it's huge legacy of astrophysical data sets. And of course, with anything where you stretch beyond, there's a unexpected discovery space. So the plan we put forward is to have a satellite with dimensions of about 4 meters diameter, 4 meters height, because it fits into a GSLV Mark III. We'll launch it to the second Lagrange point. It will point away from the sun and map the CMP sky over a few years, right? It's not uncharted territory, largely. The Planck satellite was the coolest satellite in space. It had a cryogenic detection system and, had all the challenges that we have with that. And these are solved problems, and it also went well too. What changes here is we will be breaching the capability in terms of the detectors and the ability to measure power, small amounts of power. So normally when daily experience you talk about megawatt or milliwatts, lasers, power plants. And then many of you may not know the FM radiation that gets to your FM radio is actually, the detector is very good. It detects nanowatts of power. Your cell phone detects about picowatts of power, but we need detectors that can detect attowatts of power, and even then we have to line them up in huge arrays to achieve what we want. And these detectors work at 0.1 Kelvin, right? So they are really, really cold, right? And it's a challenge to maintain from this solar panel, which is at 300 Kelvin, to this detector plane, temperature gradient such that this is at millikelvin and this is at 300 Kelvin. Okay? And there are various designs that we put forward, more ambitious one here. And I'll stop with this picture. So 10 years back, we made transformation in our understanding of the cosmology, and transformation with robustness and accuracy, with precision with which we know cosmology, with this Planck satellite which was launched in 2009. And I'm hoping that there will be a CMB mission where India will play a big role, possibly launched by ISRO. But this is still at the stage where this is a concept we have put forward and is being evaluated. Thank you, I'll stop there. No, I'm going back there. This?
So, about the anisotropy, you mentioned about perturbation. But I have a naive question. Suppose instead of perturbation, if different part of the sky have different expansion rate or something similar, so how do all other theories eliminate it, and then the...
So you probably missed a chance of being a great cosmologist, wrong field. Actually, these perturbations, because they are entropy conserving, they are best interpreted as a different expansion rate history. So there's an overall expansion rate which is the average expansion that's happening, but there is a fluctuation to that. And these density fluctuations, the source is this little deviations from the expansion history in different regions of the sky. Yes, it's true. These are what you're seeing here is this is redder and bluer, and particularly on the larger angular scales, precisely because that patch of the universe expanded by a little more or little less.
Yes, so that would be normal way of interpreting, right?
Yeah, but we know that is true.
But then can it not be all of it instead of...
Well, it's all of it. So what is happening is, on large scales, that is the source. But on small scales, physical effects take over. So this is what causes the fluctuation, but then there is matter which can respond to it, matter and radiation, and then set up these ripples and stuff like that. So that is basic physics, but what has excited that driving mechanism, all that it is doing, is essentially creating tiny differences in the expansion history, and so your expansion at some place is some 10 to the 5 minus 5 less or more than the average. So you should have come up with this idea 20 years back, that would have been great.
There was one question in the chat. I think the small kid, they're saying that mass is attracting the photon or light is bending around it. So they want to
Yeah, so it depends on how you want to look at it. Okay, in the Newtonian picture, the mass is attracting light. And there was during Newton's time question of whether a massless photon, with Newtonian gravity, whether it will bend or not. It doesn't really bend that much, and Einstein actually got that factor wrong initially in his prediction. This is best understood as gravitation lensing, where basically the space through which the photon is coming is not flat. So the straight line is not a straight line that we understand. Like, straight line on a sphere is actually one of your longitudes. It's definitely not flat, right? Two longitudes go and, intersect at the poles. That is what is happening in this. So these things are coming back and going away precisely because of that.
questions.
Hi sir. So I had a question from a theoretical standpoint that in one of your slides you showed a map of the lambda model. Yes, this one. So the model that you were using is Planck TT plus rho p plus lensing. Can you please
Sorry?
That model you are using? No?
These are the 6 parameters we constrain.
So Planck TT plus rho p plus lensing, that one. On the second column, the header.
This one?
The header of the second column.
Yeah.
Yeah.
Oh, what is that?
This is the model, right?
No.
Okay.
This is the data. This is the Planck temperature. Temperature means intensity fluctuation information. We did measure polarization in Planck. So it is used. But then with that as well as other data sets where we have measured polarization at higher angular resolution. Polarization signal is seen in some polarization signal. Weak lensing signal. So lensing causes polarization, which we have also measured. So all that put together is the data set we have used to get to these constraints.
So
now there are other combinations of data sets you can use, and largely they are consistent within error bars.
And those parameters are the standard lambda CDM model?
These are lambda CDM models. It's just written in a different fashion. It's cut out from a technical document, but this is the baryonic density multiplied by the Hubble parameter square. This is the physical baryonic density. This is the physical cold dark matter density. And omega means it's the density relative to the critical density, what we call the critical density. And that I actually like to call it the characteristic density. That's the characteristic density of the universe. This, I said, is the size of that, angular size of that ring. It translates to many other real parameters, but it's a combination of various things that are measured by this. This is something to do with the epoch of reionization and the opacity, and there's an expert right here who can tell you more about it. It's basically tells you 7% of the photons are not really totally coming transparently. They have had an interaction in between. Okay. This is the amplitude of the primordial perturbations. This is the spectral slope of the primordial perturbation. That's all I need. Rest of it are derived parameters.
And one other thing, just information. So through this LIGO detection, is this cold dark matter component has been confirmed through observation? Not directly, we cannot see it obviously, but in one of your slides you told that this cold dark matter that we have is being confirmed through gravitational wave detection. Is it?
No, I said gravitational lensing.
Sorry, gravitational lensing, yes.
Yeah, lensing is different from gravitational waves.
Yes.
But since you brought up LIGO detections or this gravitational wave astronomy will allow us to probe the dark energy sector. See, I didn't mention how much is the dark energy. That's because of that algebraic relation. I give you two of the numbers, three numbers add up to one. I have given you two of the numbers. So if you are not, someone who has not done a standard 3 or 4 of mathematics, you would know how to get the dark energy component.
Yeah, so I had actually.
You need a mic because it's ringing.
Oh, thanks. So I had actually a couple of questions. The first one is about the dark matter. What is so given that most of the dark matter candidate direct experiments have actually not measured whatever they were looking for, so what remains, and are there new ideas on what this dark matter is comprised of?
Okay, so dark matter searches, which is another amazing piece of frontier physics, frontier experimental physics, is very, very strongly constrained. And the Wriggle space for theorists is reduced so much, which is what you are referring to. It is ruling out dark matter in the most obvious things that you thought could be dark matter candidates. There are, of course, theorists are theorists. There are lots of things to rule out. One of the things are very light axionic dark matter, which may not be ruled out through these direct searches because they depend on a heavy thing knocking a nucleus in one of the crystals that you guys know better than me. Okay, and looking for phonons coming out of that. But there is also axions which can be looked at through some electromagnetic coupling, and there are huge solenoids in which they are looking for it. That's also another area. But no, we are very uncomfortable. The unknowns are really tough, and which is where people keep saying that yes, it works very well, but don't get so so much in love with that you expect that there will be a particular dark matter and a dark energy field. Okay, so I don't think he has too much against the cosmological constant. I think cosmological constant for now is a good backup, unless it does. But the dark matter, truly, we are struggling.
So I just follow up. So the LIGO experiment has now done a lot of observations on colliding black holes. Do we now have, for instance, an idea of what the black hole number density and mass distribution is, and could that at some level be a substitute, or that is just compact and it will not work?
That's very recent, yes. So there has been somehow highly physicists created a huge thing of, it must be one of the lightest supersymmetric partner, right? Because they're in love with supersymmetry, and that's what we lived with. It sort of shrouded the possibility that a lot of very senior people, I have had discussions with Ostraker when I was writing a review article with him. We have not ruled out the fact that the entire dark matter is black holes, are black holes, okay? Because black holes, again, they satisfy all the things. They are only gravitationally thing. You won't see any light emitted from them if they are not in any environment. This could be primordial black holes, and that has also come to fore because of the black holes that we have detected. So I gave a talk 2 days back, and I showed the audience that all the black holes that LIGO has detected is very distinct population from all the black holes we knew existed or inferred. I would say we knew certainly from X-ray. Okay, so this is certainly a different realm, and there are people working on this hypothesis. There are people also busy trying to rule it out. It's a very active area. Okay.
Maybe you have already mentioned, but I will read some. So in Planck, for example, what kind of cryogenic temperature has been reached using solar?
It was millikelvin, the same temperature that is needed here.
Okay.
So it is not a challenge. The challenge was Planck's observation time was limited because, again, for technical people, it is to vent helium. Okay, so we are losing helium until helium, the cryogen was there. We could run the experiment, and then the experiment should be closed down. So it was supposed to be 2 years, but we went up to 2.5 years. But that limitation we definitely want to remove because we have better ideas of magnetically cooled cryogenic things. Again, there are many here who know much more about it than me. Okay, go by name of ATRs and things like that. Sorry, you said that? Okay.
More questions? So we can end here. Let's thank
Thank you so much. Okay, good afternoon. It's my pleasure to meet all of you young people. As you will find out that I, really love meeting students. I've been doing that not only in cities but also in pretty rural places uh, because you are the future, right? And, we want to leave the people whom we can impart as much knowledge as possible. And we do it in a small way with inviting you to this National Science Days functions, but we have many other opportunities where you will be able to, interact with us. You all follow English? Yes, sir. Yeah, okay, great. So, so I think you should feel free. I mean, our institute will be very welcoming to students, young students like you, so that you can take part in various programs that Dr. Subramaniam here largely coordinates, and you already have great researchers who are going to give you talks. So I encourage you to feel free, talk, ask questions, don't be scared about asking questions, don't be shy about asking questions. There are no bad questions, so feel free to interact with us so that we can make the best of this opportunity, the few hours that you're with us. And we hope you'll be coming here more often, be excited. I think you'll go and see one of the spectacular things we have, C.V. Raman's museum next, right? So do look forward to some of you getting very inspired and interested in science. And, we are here to, help you as much as possible. Thank you so much. And thank you to the teachers for bringing your students. I know it's, it's hard to manage students on outdoor trips, but thank you all for making this possible. Thank you so much.
You guys can leave your bags here, start moving one by one, we'll just go to the museum. Okay, just leave your bags wherever you are. Don't take pen, pencil, anything, nothing. Just leave the bags on the phone. No cash, you're not allowed to take for it.
Check if his laptop is working. His laptop has his stock, mine's stock, and mine. And there are two SCM people.
Yeah, you already copied that.
So it's two talks you have.
I copied. Vinod and Deepak.
Vinod and Vaibhav.
By Vaibhav.
Deepak Mehta and Vaibhav.
Okay.
Deepak and Vaibhav.
Copied.
Both talks are there. So three there. Three and Vaibhav.
Give me your laptop. Saurabh, give me your laptop. I can. Hello. हाँ बिल्कुल अभी बैठो अच्छी लोग के check whether it's for CI. Science Day quiz poll.
Hello?
Yeah. Yeah, just ask him. Sura. SUVRA. Sura. He was transformation.
No, wait, it can't be done like this. Right? आप तीसरा
Sir, can we take photo? थोड़ा कम हो जाए.
given to Sujata. Given this I have given this person I have given the thing. I don't know his name.
Yeah, that's okay. You are given, no? Then put it.
And okay. Let's start. So the first session is about popular interactive talks. So students and postdoc researchers who work at this institute will give you a glimpse into their research. They'll try to convey some interesting science topics in the best way possible. And if you have questions, ask them at the end of each talk. We'll try to cover some questions, but then you can also catch the speaker later on, okay? So we'll have some 4 or 5 such talks. So this is Saurabh Singh. He is a scientist here, and he will tell you about peering into the universe, how we can get to know the universe, what are the ways. So let's start. Yeah.
Thanks, Sonali. Welcome, everyone. Thanks for joining today. So in this talk, I would basically be describing how we know about the universe and how do we actually study it, and most importantly, connecting it to the kind of research that we are doing at RRI to understand our universe. Before we really get into the actual history of the universe and what we are trying to do, the first thing to know about is how vivid the universe is when we look at different parts of the electromagnetic spectrum. So typically when we look at through our own eyes, we see something like this. So this is Milky Way galaxy, and something that we are more familiar with is something like this. And let me see if I can make it more interactive, which is right here. So when we look at the sky in a very remote area, we will see some parts of a structure like this. And this is nothing but our own Milky Way galaxy. And we are basically looking at it as from the edge of the galaxy. And you see lots of lights, different colors, and because our eyes are tuned to detect these. But this is not the complete story, right? We have different wavelengths that our eyes are not sensitive to. And when we build telescopes that can actually look at those wavelengths, we get a completely different picture of what our universe is like. So what I can do, I can scroll it through different kinds of wavelengths. So there are instruments that have been designed to look at the galaxy in very different wavelengths. And you can see that as we move across this whole spectrum of different lights, how the structures continuously change. So basically when we are looking at through our own eyes, we see a very small part of what it is actually. And therefore we are moving from very high energy light, which is our gamma ray, you see something, and then X-rays, visible light of course, and finally we move up to very low energy light or very low energy photons, which is finally the radio, right? So basically we have to combine all of these different observations together to understand our own universe and how it has evolved. So let's go back to the slides. We have different instruments, right? So if we want to study our universe at a very specific wavelength or at a specific light, we have to design them very differently. Some of them we can design on Earth, deploy on Earth and study. So we are all familiar with optical telescopes. This is right here, very close to Bangalore. But there are some wavelengths which we cannot study from Earth, right? So for example, X-rays, because atmosphere does not allow us to do that. So we have to build satellites and launch into space to study those. And again, AstroSat being one of the satellites from India. So for studying different wavelengths, you need to design different telescopes. The one that I would be focusing today is the radio telescope. And the great part about this is our atmosphere is mostly transparent to the radio. So we can build a telescope on Earth, and this is right here in Pune, in India, one of the greatest radio telescopes that have done amazing science. And we can build similar telescopes around the world, deploy them, and try to study the radio waves that are coming from us, from the universe. So this is what I'd be focusing today. And how we do that? So basically, if you look at the universe as a whole, this is the Illustris simulation, one of the most giant simulations that has tried to study how these different galaxies that we look around have evolved over time, right? So we know the current age of universe is around 14 billion years. And this is basically a simulation of how these different structures, these blips of light that you are seeing, actually grows with time. And this is what we are interested. That is, we know that it had some very early phases where there were no stars, no galaxies. And suddenly today, when we look at the skies, we see so many structures around us. So how did we transition from something that was so bleak to something that's so vivid and colorful? That is the evolution that we are interested in studying. And specifically at RRI, what we are most interested in is exactly this transition. So at some point we know when the universe was formed, there were absolutely no source of radiation. So it was just hydrogen gas, which is the most abundant element in the universe. But really there were no stars or galaxies back then. And we are talking about around 100 million years. And just for perspective, we are at 14 billion years. So really universe was just 1/6 of its current age. But at some point, we had these very first stars and galaxies that formed, something that we call as cosmic dawn. And this is a very crucial phase because that basically led us to the universe that we see today. So how this really happened, how these very first stars actually formed in an environment that was completely different from which we have today. So we know that there is a lot of hydrogen gas around, and there is a very specific radiation which is emitted by these hydrogen atoms. And we'll call it 21 centimeter signal without going into the depth of what it is. But what we want to do is to detect this very faint signature from the very early universe, right? And that is one of the wonders of astronomy. That is, the deeper we go, that is, the more distant objects we look at, we start to study the history of the universe. Because light takes a finite time to travel to us. And therefore, when it comes from 400 million years back, it is actually telling us what that star was 400 million years back. So that is the kind of things that we want to do at RRI. Basically detecting these faint signatures that are arising from hydrogen atoms. And for that, we have to build these radio telescopes, and we have to basically observe the skies using that. But then the story is not that simple, and that's why this is a very active field of research. So suppose I want to detect this very faint emission coming from hydrogen atom, right? And this is the time when the very first stars formed. So this is coming from a very early part of the universe. But when we actually design a telescope, that's not the only thing that we actually receive in our data. We have our own galaxy, and we saw this before how bright it is. And compared to the signal that we are looking from the very early universe, it can be 1,000,000 times stronger. So in the units that we have mentioned, these are just brightness units. The signal that we are looking for, it is around 0.1, 0.2. And in the same units, our own galaxy is 10,000, 50,000. So what we have to really do is dig deep into this data that we get to find out something about the very ancient signature that we are looking for. And to make things worse, because we are on Earth and the kind of frequencies we are looking at, we also have terrestrial emission. So the last plot here basically shows how bright Earth itself is, because we have these mobile phones, we have FM, TV stations, and they all transmit signals at exactly these frequencies where we're looking for these very primordial signals. And these are even brighter than our own galaxy, right? So basically when we observe through a radio telescope, we get a sum total of all of these. And then the question is, how do you separate out these very strong things to get back to these faint signatures that we are looking for? So it is like finding a needle in a haystack. But nevertheless, we have tried that. And the very first thing that you do is to cut down the last part, which is the interference that comes to us through the radio, television, through FM. And in order to do that, you basically go to as remote a location as possible. So if you look at experiments, these radio telescopes, where they are getting deployed around the world, which is what is plotted here, you will see one similarity, which is they are all deployed in extremely remote locations. So you can start from here. There is a telescope that is being deployed in the Arctic stations, to something in the Atacama Desert. Right now we have deployed one telescope here in Ladakh. Then you have something at Marian Island, which is one of the remotest areas in the world, midway between South Africa and Antarctica. And then we have these deserts where people have deployed these telescopes. So all of these are very remote places, and the idea to do that is basically to cut down as much of an interference as possible. So now I'll focus on our part, which is the kind of telescopes we have been deploying in India. And the first exercise that I started off when I started my research is to look for which sites are possible. And in order to do that, we had a very portable telescope, which is what I'm showing here. This is slightly non-usual telescope. So when we think about radio telescopes, we think of these dishes looking at the sky. But really, depending on what we want to do, what we want to study, we can have different kinds of telescope. And this is one of them. So we took this, we just traveled around the country, and we looked at how quiet it is, of course in radio wavelengths, how far it is from the civilization, how less FM there is, and things like those. And these are some different places, from Ooty to Andhra to Himalayas, all kinds of places, to localize which sites we actually want to observe. And finally, we ended up choosing a few sites which are shown here. And again, as you can see, no signatures of human, which is great for us. So we can have very clean data that it does not have these interference that typically we see when we, for example, do the same in Bangalore. Once we have that, the next is designing the telescopes themselves, and which is a very tricky affair because telescope can itself contaminate the data. No instrument is an ideal instrument. So we have to be very accurate in the way we design our telescopes. And as I said before, if you look at these telescopes, they are very unusual telescopes, right? Like spheres, they almost look like spaceships, but they are these radio telescopes that are looking at the very early part of the universe. So we have deployed them on land, we have deployed them on water for all different reasons, but the idea is to observe the skies and get to know about our universe. And of course, no observation can happen smoothly. So when we actually deploy these instruments, we see all kinds of things. We can see rains coming in and just drenching all our instruments. We have wildlife problems sometimes, yaks coming in Himalayas. Sometimes instruments goes bad because these are very remote locations, and then it's a challenge to fix it on the spot. Temperatures can be another problem. So we are talking about sub-zero temperatures, and therefore it takes a lot of courage to actually go out and fix some things. With the same temperatures, sometimes the transportation doesn't work. The only problem is it is in the middle of nowhere, so we have to fix it ourselves. But in midst of all these hiccups, we finally are able to conduct these observations and get the first light. right? So we are able to observe the universe with our telescopes deployed in extremely remote locations. And that itself is a great feeling. And so we have skies like this where we have observed, this is one of the locations in Ladakh where we had observed these tiny tents are where we had actually stayed. And we see amazing skies, very less interference from radio, but also light-wise, because these are away from any human civilization. So you get to see the entire what the galaxy is and what structures exist in the skies. And I'll just jump on to the last part of my talk, which is once we have the data from pristine locations like this, another challenge is how do you remove all these contaminations? So okay, we have removed human interference by going to remotest of the sites, but then we still have our own galaxy. We live in a galaxy, so we can't escape it. So we have these observations. Then there is another round of research in how to distill that data, remove all of this haystack to finally get down to the needles, which is what I'm showing here. So that is the kind of exercise that we do. And the final slide that I'll show is finally escaping Earth altogether, which is something we are doing at RRI, which is we have gone to the remotest of locations, but that's not good enough. So one of the quietest sites in the solar system actually is Moon, because when we have a telescope which is on the far side of the Moon, it is shielded from both the Sun and the Earth. And both of them are primary sources of contaminations in our data. So we have proposed an experiment called Pratyush. It is funded by ISRO. So we are developing this radio telescopes that will fly in space in lunar orbit, and it will conduct these radio observations of the universe from the far side. So with that, I'll close and take questions. Thanks.
Let's have just one or two quick questions. Yeah? Do you have?
Don't be shy.
Ah.
Questions. There are no bad questions. Any question will be taken by someone.
Yeah. Has been. Yeah.
Speak in the mic. We are recording.
Sir, so this Pratyush which is mentioned here, this will be in the orbit of the moon or it will be on the surface of the moon?
It will be orbiting the Moon. So the idea is that when it's on the far side, when it's not facing the Earth, it will actually look into the sky and do these observations of very early universe. And then when it comes, because it also needs to transmit the data, so when it comes on the other side, when it faces the Earth, it will do the rest of the things.
Sir, if there's any disturbance after the launching of any satellite, what would be the process of it?
Right. That's one of the disadvantages of space missions. When you have launched, there is very little that you can actually do. Of course, people can take corrective measures, but it's difficult. Therefore, for any space missions, it is essential to demonstrate its working in the lab. We have to go through a series of tests to make sure that it will actually work in the space before we actually fly it.
Sir, while you're collecting some data from your supercomputer MacBooks and all, like what type of backup do you have if you lose data?
Great question. It's a very non-trivial question because the data loss is really one of the most nightmares of all researchers. So we basically have, for example, when we go to sites like these, we don't have internet. So we basically have multiple rounds of backups. So we have data on our computer, but we also carry these external hard disks. We have a primary backup, and just to be double sure, we also have a secondary backup. So just in case if one thing goes bad, we have other options. And the moment we come back to the civilization, we upload all of that on cloud, so it is safe for a longer time.
Let's thank Saurabh for such a wonderful talk. Our next researcher is actually online, and Santra, can we?
This other machine, yeah.
He was really keen, so we said that no only physical, but he was really keen to give the talk. So it's an online talk. We'll just put up, and he wants to tell us about the randomness in large numbers. So I hope you will enjoy it.
Ayan, can you hear me? Ayan, I think you are muted.
Okay, sorry. So am I audible now? Okay, okay. So now that you've seen the face behind the voice, I'll go on to the sharing mode. Yeah, can you see my screen all right now? Okay. So I'm a theoretical physicist, and today in this talk of randomness and large numbers, I'll not really talk about what I work on, but I'll try to give you some basic ideas about the subjects via very simple things. Okay, so let's start with a very simple setup. Okay, so suppose I have this lattice kind of a thing, a structure basically, and I drop a ball from on top of this structure, and at each this top vertex of the triangle, the ball can go either to the right or to the left. Okay, and then I let the ball run through and let it collect in one of these boxes. Okay, so where will the ball end up? Okay, so you can answer, some of you may answer the left box or the right box or somewhere in the middle, but the point is everyone would be right, because the where the ball ends up is completely random, because it can take any one of the paths and just go and sit in one of the boxes. Okay, so the final result is completely random. But instead, what if I have a collection of balls? Okay, so this is the setup now. It's the same structure which I showed you earlier. So I have a funnel like thing where I like trap a lot of balls and let them go and I let them collect in the boxes that I had shown earlier. Okay, so this particular setup is called a Galton board. So it was invented by Sir Francis Galton, who was an Englishman, but he was this lot of things. So I kept just this to show you that nowadays, I mean, you don't expect people to do so lot of things together. I mean, he did quite a lot of things, and he was brilliant in all of them. Okay, so yes. So what happens to these balls? Now, when I let them drop these balls, what I see is you go again. So it drops, and every time it drops, the balls collect in a way that it forms a particular shape, right? It always, there's this outline, it always ends up something like this. So it's interesting, right? Because we just now saw that at a single ball level everything is completely random, but when you are taking a collection of balls, you are getting shape some particular shape every time. Okay, so what's going on? So now let's do a little bit of counting. Okay, suppose I have this one triangle, and the boxes are just after my first level, so I'll call the levels as the levels of horizontal triangles. Okay, so in what way can it collect in the two boxes? So then I have two boxes, right? So in what way can it collect in the two boxes? So it can either go this way or it can go this way, and it can collect here I mean, there's just one path, it can go here, or it can go here in this one path only. Okay, but what if I have now two levels of these triangles? And so how many ways can the ball go to positions A, B, and C now? So can somebody quickly answer? Anybody in the audience? So I'll just show you one. So this position A goes only by one path, only because if it goes like this, it cannot reach A. It can reach A only by via one single path. So B, C, can anyone guess or say how many ways it can go to B or C, end up in B or C? I didn't hear. So is anybody answering?
Two, sir.
It's very simple. Yeah.
Only two balls can go to B maximum.
Yeah. Yeah. Did somebody say two ways into B and one way to C, right? I heard
Yes,
correctly,
sir.
if I heard correctly. Yeah, so you are correct. So it can go to A or C in only one way, and it can go to B in two ways. It can come from here or it can come from here. And if I increase the how do I remove this? Anyway, now say I increase one more level of the triangle. Okay, so then again at the ends it can go to the ends it can go in one way, and to the middle you now see it goes this one it can go in three way, the ways are marked with green, and again to the yellow also it can go in three way. Okay, so it appears as you just go on keep adding on the levels, it keeps forming this pattern. So one and then one and then 1 2 1, and so there's something about in this pattern. So have any of you ever seen this pattern before? Is no the answer?
Yes, sir.
You have seen this?
Yes, sir. In mathematics.
It's the Pascal's triangle. Okay. So what happens is, so there's one here, and whenever you go to the next step, what you do is this carries on, and the next number is basically the sum of the things in the previous two. So here 2 is the sum of 1 and 1, and then again you get 1. And then here it's 1 plus 2 comes 3 here, 2 plus 1 3 here, and again 1 here. Okay, so as you keep increasing the levels of these triangles, you generate this Pascal's triangle. Okay, and it goes on. Okay, and the number of balls at a particular box, if you have say a large number of these levels, is actually proportional to the number of paths that can lead to the box. Okay, so you have a maze and you calculate the number of paths it can go to one particular box. So your net weight it will be of the number of balls. Is anybody saying something? No. Okay, so the number of balls in that particular box would be proportional to the number of paths that can lead to the box. Okay, and so here I have plotted this number these numbers. If I had 9 levels, and you automatically see the pattern which we were seeing in the Galton board experiment, right? This pattern emerges. Okay, already. So basically, there are still the fluctuations. You can see the red line and these are not quite same. But as you keep on adding the number of balls, these will become smoother and you will have something which is a Gaussian distribution. Okay. If you're doing physics anytime later after your 12th boards and so on, this is something you will encounter surely. Everybody does, and it's right. It's named after Carl Friedrich Gauss, the famous mathematician. Okay, so now this is a very important concept in physics, which is called random walk, which has numerous applications in physics, mathematics, biology, economics, ecology, and everything. Because it's quite inherent in these subtopics. Okay, and it's also often called a drunkard's walk, because imagine you have a drunk person coming out of a bar and he doesn't remember where he'll go to. Okay, so he goes forward some distance and then he remembers, no, my home is that way, I'll go there, and then he goes the other way, and then again at some point of time he remembers, oh no, I need to go the other way. So that's why it's also called a drunkard's walk. And so the takeaway message from here is random events basically lead to predictive patterns, and these predictions become better larger the number of events or subjects. Okay, and from there I'll quickly jump to something which is closely related to stat phase. So basically, in a solid, liquid, or gas, you have a large number of molecules. So what do? You don't solve Newton's equation for all the particles. Okay, so there are huge number of particles, and you can't calculate the Newton's F equal to ma for all of these. Okay, but again, you can predict the macroscopic behavior. Macroscopic behavior, the emergent behavior which we see. Okay, you can predict that behavior from a collection of a large number of molecules.
Ayan, can you finish in the next 2 minutes?
Yes,
okay.
yes, sure. So it's a collection of large number of particles. You can predict this emergent behavior when you have a large number of particles. Okay, and this is in a way is similar to the counting problem which we just saw, and this is the basic basic behind the idea behind equilibrium statistical physics. Okay, so if you have the total number of particles, volume, and energy of a system of particles, say a large time is 23 order of particles, and you have to count the number of ways in which they can be arranged so as to fix these constraints. Okay, so NVE, you fix them, and you can see how many ways you can put them into these kind of boxes. Okay, and the number of ways you write it in something called W, say. And then you can define a function which is called an entropy. I think you must have heard this in sci-fi movies and so on. So entropy you define as k log of omega, W. And then when you have this S, you can calculate specific heat conductivity, predict phase transitions, and everything from it by taking derivatives or integral relations from this. Okay. So this is called the Boltzmann prescription, and so that's all for my talk. So the take-home message is basically what appears random to naked eye is always not completely random. There's hidden information that can be extracted, and the law of large numbers, which we physicists typically call the thermodynamic limit, can lead to very predictive laws.
Okay, let's have let's have questions.
Sir, like what type did you feel interesting so that it attracted you to do research on this?
I cannot hear the question.
He said that what did you find interesting that you are doing research on this? What was the motivating part?
Okay, so the point is, for this example, you see, you have a liquid, you have a large number of liquids, liquid molecules. So you don't solve the Newton's equations, right? You just do what you see is you count. There's a number of counting patterns. This counting can be very tricky and very difficult. And then you just writing these W's and these functions are, I mean, not trivial for all
No,
kinds of systems.
Ayan, are you? Can you hear me?
Yeah.
So question is, what motivates you in your research? Why are you researching on?
That's what I'm answering.
Acha. Okay.
Okay. So I mean, to predict new phases of matter. Okay, if you are doing these exercises and there are some things which you cannot, which you haven't seen yet, and that you can predict from here, the kind of phase transitions in matter. So water to water vapor is one kind of phase transition. There are numerous other phase transitions, and magnetization, you have magnets and non-magnets. Okay, all these you can predict from here. So it's basically learning trying to learn what is in the basic, what is in the, I mean, how these matters change among themselves and so on. The different states of matter, for example.
Okay, let's thank Ayan for such a wonderful talk. And our next speaker is offline. He is Deepak Mehta, and he'll tell you about the most powerful computer ever.
So hi everyone, good afternoon to all of you. So do you know the name of the most powerful and the most complex computer ever? So I'm not asking about the computational power of that computer, I'm just asking about the intelligence of that computer. Anyone? So like one more hint, that is natural computer. Yeah, you are right, that is human brain. So my name is Deepak Mehta and I'm working here on cell biophysics lab and I'm doing research in neurons. So our brain consists of 100 billion neurons. Please don't count the zeros. And with 1 million billion connections, and we call these connections synapses. I will talk about these synapses in later slide. So let's begin with the very simple fundamental things. What is neuron? So neurons are cells which transmit signal from different body organs to our brain, and then brain process that signal and then again send back to our different organs. So this is the structure of neuron. You can see here, one sec. Yeah, you can see here, this is the main cell body which is known as soma, and these branches are called dendrites which sends the signal, and this large branch is known as axon which transmit the signal to the next neuron. So what is this signal? Let's come to that. So you know, to transmit any signal we need two things. First we need one source. In other words, we can say first we need one battery, and battery is something which separate to different kind of charge, positive and negative. So what is the battery here? So that battery, let's suppose, consider one example. When I'm pressing my hand, what is happening here? I can sense the touch, no? So how I'm sensing that? So what is happening here, when I'm pressing my hand, so basically I'm separating some charges. And in case of neuron, these charges are called, these charges are calcium ions, sodium ions, potassium ions. So once we separated them, these separation of charge act as a battery source. Then to transmit an electrical signal, we need some connecting wire. And that must be conducting. But neurons are the material by which neurons made, that are kind of dielectric or insulator. So our body continuously work on neurons to maintain some charges on them, and for that our body every day takes almost 1/3 of total energy to make charges on neurons. So our only brain takes 1/3 of total energy. So when an signal propagate through these neurons, it's look like this. This is known as action potential, and if we will block this signal somehow, we can stop the sense of we can stop the feeling of sensation. That is exactly happen in case of local anesthesia. So when we took anesthesia, generally we block this signal. So, and you know, neurons are the longest cells in human body. There are some cells, some neurons, which are even longer than 1 meter, which connect your toe to your spinal cord. If suppose this signal will not be an electrical signal, then what will happen? Let's suppose this is some diffusive signal. Diffusive signal means that is simply moving, simply flowing inside your cells. Then if you want to move your leg, then you will move your leg in next 700 years. That will be too much slow. So thanks to the electrical signal, you can do that within fraction of second. So the speed of signal inside neuron is approximately 70 to 120 meter per second. So it's quite fast. And the next thing, when this signal propagate through axon, it will jump to the next neuron. So let's see how it will jump. So this is the axon terminal from where it will jump to the next neuron. So initially in the growing stage, it's look like this, and it's called growth cone. So initially it's find its neighbor neurons where it can bind, and once it's find its neighbor neuron, it's bind to them and it's form synapses, connection. These are the connection, and in brain there are 1 million billion connections. So let's zoom it, what is here. So you can see this is the axon terminal, which we call presynaptic terminal, and this is the terminal of the next neuron dendrite, which we call postsynaptic terminal. So, and these spherical bag-like structure, big sphere, are known as vesicle, inside which neurotransmitter and hormones are packed. So what happened when an electrical signal arrives here, this vesicle fuse with the membrane, and the neurotransmitter release into this gap. And then next what happened, these neurotransmitter attached with these receptor on the next neuron dendrite, and they regenerate that electrical signal again in next neuron. So what is happening here, initially an electrical signal came here that is converted into a chemical signal, and then that chemical signal again converted back into the electrical signal. So these neurotransmitters are chemical, and you must heard about these chemicals. These are dopamine, adrenaline, you must heard about this, no? So yeah. So now let's see from where this vesicle came here. So actually this vesicle is prepared at here on the soma, main cell body, which is very far from the terminal. So how they came here? So this is the vesicle which is coming from cell body to the axon terminal on some straight road. We call these roads microtubules, and the protein which is carrying this vesicle is known as motor protein, and these motor protein can move in both directions from cell body to the axon terminal, and they can move also from terminal to the cell body. So now, do you know what happened in our brain at neuronal level when we learn something new? So initially it is very difficult to do that thing if you are doing something new, so you feel very difficulty. But after again and again, if you do practice, we become expert on that. So why it is happening? So the reason is that you can see here two neurons. This is before practice and this is after practice. So you can see in the case of after practice, there is something extra on the axon. These are called myelin sheet. So when an action potential continuously moves through axon, there are some myelin sheet formation. These cells are called myelin sheet. In case of brain, these are called oligodendrocyte, and in case of PNS, these are called, PNS is the, in our, the neuron system is consist of two parts. One is CNS, one is PNS. CNS is the brain part and is spinal cord, and PNS is rest of it. So in PNS, it is, these cells are Schwann cell. So these cells form when we do something regularly, again and again. So what is happening here, before the practice, when some signal will move, it will move continuously like this. But after practice, when there is a formation of myelin sheet, the signal will jump like this, from here to here, node to node. So this jumping signal is faster than before one. So that's why now the exchange of information between different part of body is faster, and that's why we do that thing very easily after practice. Yeah. So I want to end my talks with one interesting fact. You know, all our body is made of cells, and the most of cells are non-dividing. Sorry, dividing. Dividing cells are those cells which divide themselves and regenerate themselves. So the interesting fact is that when our body, you know, our body is entirely, almost entirely new after every 7 years. Who I am, I'm not that before 7 years. So almost entirely new, we are almost entirely new after 7 years, because all the old one cells replaced by the new one. But brain cells, neuron, are non-dividing cells. This nature of neuron is good for memory storage. Otherwise, we will lose our memories if neuron cell also divide. So this brain memory is not something like hard disk in a CD, which is we know where which folder is where, which file is where. But this memory is very diffuse. It's very complicated. So we still don't know how it is work actually. But the one thing is that your memory will be stronger if the connection between these neurons will be more. Higher the number of connection, higher your memory will be higher. So this is the thing, and this is this memory is amazing. We don't know about it too much. And yeah, that's all. So thanks.
Okay.
Any questions?
Quick questions.
Sir, as you said, some of the things in memory are theory and some of them are proved. Can you share?
Sorry, what?
As you said, some of the things are theory, like memory and all are theory. Like it is not proved yet, but some of them are proved.
Yeah.
So can you just tell us some experiments in which you had experience while you were studying?
Yeah. So there are some experiments which showed that memory increased when these synaptic connection between neurons are stronger. Some experiment with rat and mouse have been done, where we saw that before we trained them and we saw before and after. We saw that these connections are stronger after when they become trained in something. So these connections are stronger, and we lost we forget many things. No? This happened because of the loose connection between these neurons. So we know these things, but we don't know where. We know that which section of brain store what kind of memory, but we don't know exactly what is where stored. It's very complicated. Still working on it.
Let's thank him again for such a wonderful talk.
Thank you.
And our last speaker is Vaibhav Singh Parmar. He will tell us about trapping tiny particles using laser.
So, hello all, good afternoon. My name is Vaibhav. I am an experimental physicist at Rheology and Light Scattering Lab here. So, I want to talk about an application of laser that is very useful in terms of tiny force measurements. So, that is I want to talk about trapping tiny particles using laser. So, first, this is a picture that you all must have seen in some sci-fi movies, where this is a tractor beam where a UFO is lifting a cow. Actually, this is not a real picture, but so is it possible to do something like this? Is it possible to control movements of objects, movements of some objects using light? So yes, it is possible, but not for large objects. We can control the movement of small particles that are quite small, micron size particle, using laser light, that is high intensity laser light. And recently in 2018, Arthur Ashkin won the Nobel Prize for developing this technique that is called optical tweezer, and it is useful for this trapping of micron size particles in using high intensity lasers. So before going further into that, I would like to talk about some basic properties of light that are so simple that and that are the main physical processes involved in this optical tweezer process. So one of that is the refraction of light. So what happens as light travels from one medium to another medium? So since each medium has different refractive indexes, that is the property that is inherent of the system, inherent of the medium. So as light goes through one medium to another medium, it changes its direction. It changes its direction, and the amount of change in direction, that is the amount of bending, will depend on the difference in the refractive indexes of the beam. So, and the other fact is that light is made up of photon, and then since it is made up of photon, it carries momentum. So initially we only know that light is a massless thing which does not push anything. So, but it is not true. Light in terms of particle theory, light is made up of photon, and it also carries energy and momentum, and it can be used to push or pull something. But since the effect is quite small, and in daily life we can't comprehend that effect. That is quite small. So it is in the range of 10 to the power minus 7 newtons. So for comparison, if 1 kg object will exert a force on Earth of 9.8 Newton. So it is quite small. But so let's see. So there is a mirror. So if a light shines on it, and then it gets reflected due to this mirror is 100% reflectance, and due to this change in direction of the light, there is a change in momentum or change in momentum of the light. So since momentum should always be conserved, and then for that to happen, the mirror will also feel a force, and that force is due to this light. So light can also push things. So and this force is called this Fs, which is this radiation pressure, and I'll call it light pressure. So, and this light pressure can also exert on this spherical object, which are this transparent object, due to this refraction that I told about. So if light is coming to this object, and it is getting refracted, and then it will pass through this object through reflection. And since the light has changed its direction, so there is this change in momentum of light, and since the momentum has to be conserved, so the particle will feel a force, that is, since we know Newton's second law, F is equal to dp by dt. So the bead will feel a force, and since this bead is quite small, so the effect of the forces could be comprehended by this particle. So, and that force is going to this direction. So if we put this same beam in front of laser, that is just a light with high power. It is a coherent beam and a high power beam, and it has this. Okay, so it has this intensity variation so it is more intense in the center, and as it goes, it is less intense. So this kind of beams are called Gaussian beams. So if we put a bead or a transparent object in a sphere in the mid of this laser, so what will happen is that as the light will pass through it, light will refract, and then in both sides, light is refracted in the both sides. So the total resultant force will push the particle in the front direction, and this force is the scattering force. But for this same laser, what if this the bead is not completely at the center? What if it is little off center? Then what will happen? So in this case, the light that will go through the center, and then it will get reflected from the transparent bead. It has more intensity from the center. So what will happen is that there will be a restoring net force towards the center of the beam. And so what we are talking about, we want to trap some particle. We want to control the movement of small particles. So we want some restoring force. So if we move something, it will come back. So in this case, there will be a restoring force which will act downward. I am calling it Fg. G means gradient, which is just since it is a change in intensity. So the force is acting. A force is acting due to this change in intensity. So it is a gradient force. And at the same time, there is this scattering force that I talked about earlier. But the effect of gradient force will be to put the particle at the center of the beam, so to the region of high intensity. Similarly, if the particle is off-centered on the other side, then the light that is going through the center and then reflecting through this sphere, it is more from this upper side, and then there will be a restoring force which will act upon the upside, and the beam will go at the center. So here, particle will likes to be at the region of highest intensity. So since we want to trap a particle, but here only we have trapped the particle in this line, so it can't go in up or down, but but there is this scattering force also that will act, and then the particle is not actually stable. So how can we make a particle stable in this case? So particle can't go in a two direction, but it can go in the other in the direction of laser beam. So one way is to just put a laser on the upper direction, and then the gravity will act, and then this scattering force will act, and both can balance. But that is quite unstable. That is not practical, because if any small disturbance will create, so that is an unstable equilibrium. So we want a stable equilibrium. So the idea that Arthur Askin gave is that to make a highest intensity point instead of highest intensity line, just put a high power lens in front of laser. So what lens do? A lens converts the light, and then there will be a point that is highest intensity. And if the lens is powerful enough, and then if we put the bead there, then the bead can't, even though the bead will feel the scattering force, but since there is a large gradient force, and the gradient force is larger than the scattering force, we will achieve this optical trapping. So in this case, particle can't go anywhere. It is moved in this three-dimensional space. And actually it has many applications in our field, where we look at these tiny particles, and then we see the forces and we see the movements of tiny particles. So one application is this motor, kinesin motor. As in the last talk, Deepak showed you that these motors will walk on this microtubule. So and then with this optical tweezer, what we can do, we can make measurement of these things. We can make this. We can just put a bead and we connect to the kinesin motor, and okay. This one. Yeah. So here is this measurement. So you can see that this kinesin motor moves through this road, right? So this bead can actually measure the movement of this kinesin motor. This motor that is quite small. That works in our body. So you can see this. This kinesin motor can take steps. Small steps it takes in some time. It relaxes, and then at some time it takes steps, and then the position is increased. So position increased, it relaxes for some time, and then it takes another steps, it relaxes for some time, and then this motor takes another steps. And these quite small, so this is in nanometer range measurements, and that can be made using this setup. And this is quite simple setup. So at last I would like to demonstrate something that is some simulation thing. So what I will do, I will just show a Brownian particle that will just do Brownian motion in a water, and then I'll show that what if I turn on the trap, what can I do with that. So this is not my simulation. This is I taken from this FET, that is a website. Let's first turn off the laser. So laser is not here. The particle is only doing this Brownian motion. And Brownian motion every small particle will do because of this random kicks from the medium molecules. So, but if we want to control this particle, if we want to move this particle however we want, if we want to see that what the particle is feeling in this environment, small environment, we can't do it. But if I turn on the light, so if I turn on this laser light, and then there is this lens, now the particle is trapped. Particle is trapped, it means that I can move the particle however I want in this small space, and it is quite nice because this particle is quite small. We can't see this particle, but we can control its position, and we can measure the forces in quite small ranges. So let me see this, show this in terms of this potential energy curve. So potential energy curves are just shows that where the particle wants to be. So lower this and lower this line, the particle will always want, or the system will always wants to be at that point, and system will try to reach a point of lowest energy. Then this lowest energy points depends on the power of the laser. So if I increase the power of the laser, this energy points actually goes down, which means now the particle is trapped even more with more power. So essentially the trap is acting as a spring, And if we increase the power intensity of the laser, it means that the stiffness of spring is increased.
Okay,
Yeah.
let's thank Weber for such an amazing talk. One question.
So while in laser light, in blue cut lens, laser light will not travel.
Which lens? Sorry.
Blue cut lens.
In which lens?
Blue cut lens.
What are these? So, no. So I didn't get the question actually.
They're saying.
I don't know.
She's saying that there's this lens introduced by the lens card, which, I mean, it's worn while using computers to block the blue light that's coming from the screen.
Yeah.
So she's asking how that works. Am I right? Yeah.
So for those lenses, actually, lenses are made to in that case, lenses are made up to clear your vision. And since the blue light is harmful for your eyes, so in that case, I think they just put a coating on the glass so that only the light that passes through is of higher wavelength. So the coating will absorb or reflect the light of in this blue regime, and then only you can see the yellowish light part.
Yeah, let's thank him again.
But that lens will also make this. So in this case, the lens needs to be very powerful because the gradient force needs to be very large. But that lens also creates this converging lens. Yeah.
Okay.
And depends on the problem. Yeah.
So let's thank all the 4 speakers. Anyway, it also shows you the range of things that people do at RRI. They get into the brain, they know about the universe, so it's really exciting and really interesting. Now the next part is quiz, and we have prepared a very nice quiz with 4 rounds, 10 questions each. So what we want for that is that you, 4 schools are in 4 corners. So yeah, we just want that you have a gap between sit school wise, one school here, IASC Hebbal here, IASC yeah. So IASC Hebbal can come here.
आज साइंटिस्ट के लिए पर्ची दी थी ना, तो किसी ने नहीं दिए, तो बोल जिसके पास है वापस कर दे।
तुम लोग क्विज तो सेट करो. Okay. Okay. KV Hebbal is here, and this is which one? Stellar Maris is here. Then IASC, KV IASC. So go to the back, leave at least 2 rows, and then Karnataka Public School, please go there. Leave 2 rows. There should be a clear distinction. Don't sit here. Make some distance. So come here. KV Hebbal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. This is which one? Stellar Maris. Yeah. Yes, Stellar Maris. KV Hebbal. So that is KVIASC, right? Leave 2 rows. Leave this. What you are which one? Huh? Oh, KPS, na? Go there. Don't sit here. Make a distance. You come here. You 3 people. You can come here. Clear distinction. Leave 2 rows in between. You can come in this row, in this blue bag row. Yeah, in this row.
अरे इंस्ट्रक्टर का वाला स्लाइड है, आएगा आराम से, हम कुछ काम नहीं करेंगे.
टीम ए का टीम ए भी हम
पेन पेपर लाऊंगा, कोई कर लेगा, ये माइक ऑन है, ठीक है.
So, Stellar Marriage, you are team A, okay? Just remember that. Team B. IAS, हाँ. KV IASC team B, okay? Karnataka Public School team C, okay? And KV Hebel team D, okay? Just remember that. You were given some chits for if you have some question that you want to ask a scientist. So if you still have those chits with you, just you can give it to me, give it to yeah, just give it to the nearest volunteer. Yeah. Okay. Okay, I think our quiz master will take from here. He will explain you the rules and then how to play it, and whosoever raises that, we will keep our eyes open, and whosoever raises the hand first will get the chance to say the answer. But there is negative marking, so only raise your hand when you are sure of the answer. Okay, otherwise you will make your team lose marks.
Hello everyone. So I will quickly go through the rules. There are 4 rounds, 10 questions per round, plus 10 for a correct answer and minus 5 for an incorrect answer. So whosoever feel that they know the answer, just raise your hand as quick as possible, and the volunteers will see through and you will get to answer your question. Okay?
Mobile phone, you are supposed to keep it in your bag. If you are seen using one, it will disqualify.
Okay, so and if a question is answered incorrectly, that question is collapsed right there and it will not be passed on. Okay, so yeah, and so before starting, the Science Day is celebrated, as you all know, for the discovery of Raman effect, and with this we will start our first round. So ready? Okay, we'll start something easy. We are living in which galaxy? Oh God. 10 points for your team, and be quick guys, be quick, okay? Chalo, for the next question, it's Milky Way. Carbon dioxide plus water plus sunlight. One more thing, please don't answer the question before raising your hand. You raise your hand and they will tell you to answer, only then you answer, okay? Chalo. It's okay, it's fun. Photosynthesis. Hands become warm when we rub them together. What is the reason? Who is good? Okay, she answered. Okay. Okay, okay. It's frictional force. Sorry, ma'am, we have already designed it, so I think it's. So yeah, they are able to see. So it's okay. Okay, so we'll go on for next question. What is the most abundant element in the universe? That correct, 10 points. It is hydrogen, and pasteurization was invented by this one. Correct, 10 points. Louis. Yeah, yeah. What element does diamond contain? I I think we'll dissolve this question, but anybody can answer. True. Okay. Who discovered the 4 biggest moons of Jupiter? They raise your hand. True. Shall I- That's what we can go ABCD from next round.
Let's go ABCD.
From next round we'll go ABCD.
Yeah, from second. ABCD.
From
Tough to
There,
because it's a
there are
bit
3 more questions. After that we'll go ABCD. Right? Only 3 more questions left. So okay. At what time of the day will the shadow disappear? Okay. Correct. He got Nobel Prize for the explanation of which phenomenon? Correct. Just bear for me with one question, then we'll go A, B, C, D, okay? It's for the explanation of the photoelectric effect. First woman astronaut of Indian origin to go to outer space. Yeah. Okay, from now on, yeah. So this ends the first round. So from second round, we will be going. Yeah, scores will come. So we will be going team A, B, C, D, right? Okay.
Right now, team B and team D are tied up at 40 points, and team A and C are tied at 20 points. But you can easily cover it up, and now we will not go with this raised hand. We'll go team by team.
Fine. Yeah. Okay. Now, is it team A and team B, team C, team D? Okay. Now for the second round, yeah, it's Kalpana Chawla. For the second round, team A will answer, right? Which of the following is a scalar quantity? Yes. Correct. Okay. And the next question goes to team B, right? Identify the following element. Correct. Team C. What is Ramanujan number? Main. No. Shall we pass? Pass. Correct. Do you know the reason for this 1729? Yeah, so the Ramanujan number 1729 is the smallest number which can be written as sum of two cubes. And there is an interesting story for this. When Ramanujan was really ill, his professor Hardy came in a taxi. That taxi had this number called 1729, which Hardy felt that it's very, it's not very good number, it's giving some bad sense, etc., etc. So he went to Ramanujan and he told that, see, I have came in this taxi 1729. Then Ramanujan suddenly told, no, 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 this 1729 is very unique number, and he gave this explanation right away without any delay. So that's how this number got. And I'm so inspired by this story that my phone number last 4 digits reads 1729, and even my Gmail has last 4 digits 1729. Chalo. We'll go to the next question. Team D. Which is the least dense planet of our solar system? Be careful. Correct. And Saturn is the density of it is actually less than water, that it floats if you have water, if you keep it in water, okay? So, question number 15 goes to team A again. Which physics law best describes the following GIF? Correct. That's called as Newton's third law. Yeah, right. And question number 16 goes to team B. Ready? Yes. Correct. And yeah, so regarding Abdul Kalam, these are the 3 books which he wrote, and the last book I had read, it's very small book, I think you can start reading it, it's very good. Okay? Question number 17 goes to team C. What is the speed of a geostationary satellite with respect to Earth? Okay, I guess we have to pass it. So, any answers from team C? No? Okay, team D. No? Pass it to A. Pass it to B. Okay, the answer is 0 because it is geostationary satellite. So with Earth, it rotates along with us. So yeah, it's 0. Question number 17 goes to team D. Ready? Oh, sorry, 18. The following image is the first image of which type of astronomical object? Your answer is wrong. Team A. Any answers? Team B? Correct. It's the image of a black hole. So, yeah. And have you watched this movie called Interstellar? Yeah. So, please. It's fine. We'll go to the next slide, 12 questions. Next 10 questions are 12 questions. It's fine. No. And it was a past question, right? Okay, we'll go to the next question. The following are together known as what? Team A. Yes. These three are together known as what? Correct. Next to team B, question number 20. In which of the following the object is at rest? Correct. We will not count the rounds. We'll directly go to question number 21. Don't consider this as rounds. They are just number of questions from now on. So don't consider this. So we'll go to next question, and it will be answered by team C. Okay. Litmus paper dipped in soap water turns into which color? Correct. Blue color. Yeah. And question number 22 goes to team D. What is the main reason behind the seasons on Earth? See the question, see the... Huh? Exactly. The tilt in the axis gives rise to the seasons. Okay. Question number 23 goes to team A. Okay, this is the answer. Which process is responsible for sun to shine? You can guess an answer, but one answer. Correct. It's called nuclear fusion. And question number 24 goes to team B. Compressed or elongated spring has which form of energy? Correct. The next question to team C. That's the potential energy. Guess the phenomenon. Teams. Huh? Correct. Aurora formation. Question number 26 to team D. The broken pieces of magnet will attract or repel. Correct. They attract because of north and south poles. Yeah. Question number 27 goes to team A. The ballet dancer rotates faster when they fold their arms. Which conservation law is responsible for this? Yes? Anybody? No. Pass to team B. Correct. Conservation of angular momentum. Question 28 goes to team B. What would be the speed of light in a medium with refractive index greater than 1? See the options and answer. No. Pass to team C. No. Pass to team D. Nah, it's just an answer, right? You can just answer. See, why is that so? Yes, the velocity of light is correct. The velocity of light in vacuum is 3 into 10 power 8. So you had to just choose an answer which is less than 10 power 8. Yeah. So question number 29 goes to team C.
I think that boy has given the most intelligent answer compared to the other.
Yes. So question number 29 to team C. Weight of moon is 1/6 of weight of earth. If mass on earth is 66 kgs, then mass on the moon is team C. Huh? Wrong. A pass to team D. Huh? Yes, that's the correct answer. The mass will remain same. It's the weight that changes, and it's depicted in the picture there. It's the same girl standing on both, but the weight is changing, but the mass is same. Question number 30 goes to team D, right? What is laughing gas? Wrong. 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 Correct. It's nitrous oxide, and so we'll go to question number 31 from here, and team A. So team A is your question. Which type of mirror is this? Correct. Who discovered X-rays? Team B. Pass. So pass to team C. Yeah, correct answer. It's Röntgen. And actually, the picture which you see here is the hand of Röntgen's wife. So when he first discovered that there are X-rays, so first he filmed his wife's hand. And actually, when his wife first saw the picture, she literally freaked out, saying, "I saw death," because nobody living has seen their own bones, right? So this is the picture, and yes, it is Röntgen. So question number 33 goes to team C. Team C. It goes to team C, right? Yes. Question number 33. What will happen to water level inside the red beaker after some time? Just think. Yes, team C. Yes. Yes, correct. And why is that so? Okay, so yeah, basically the candle eats up the oxygen and the pressure inside is decreased. So that's why the level raises. Okay, so that's question number 33, team C. And question number 34 goes to team D. Needle of compass points towards north and south directions. Why? It's because of the Earth's magnetic field. And can you tell me on the North Pole, what is the Earth's magnetic field? Correct. Okay, team D gets the points. And question number 35 goes to team A. It's not South Poles. Which of them will hit the ground first? There is a 10 kg ball and there is a 5 kg. Correct. Both of them will hit. And do you all know about this story of Galileo dropping the two weights from? Yes. So it's correct. It's both. And we might get a chance to see a nice video done by NASA. So we'll see. Question number 36 to team B. In a toss of two coins, what's the probability of getting heads for both of them? Correct. It's 1/4. So question number 37 goes to team C. What has happened to the light in the fourth picture? Do you want to give an answer? Team C? I heard something. Correct. It's total internal reflection. That's correct. Question number 38 to team D. It's total internal reflection. Cos 0 into cos 1 into cos 2 till cos 100. What's the value? That's correct. So 38, team D gets the points. So last two questions. Question number 39 goes to team A. Yes, that's the reason. Cos 90 is. All the beakers are of same height. Which of them will get filled first, A or B or both? Huh? That's not the correct answer. That's not the correct answer. Correct. Because the pressure on both A and B is same from the atmosphere. So both of them will get the water will get filled at same level. Okay. So the last question to team B. To cover up. See the picture, a student drops the ball, so the student is there, and choose the correct sentence. The person on the ground sees the ball moving vertically down alone or moving downwards and forwards. Team B. No, that's not the correct answer. No, it is not downward and backward. I will explain it to team C. Okay, I'm sorry. So the reason is, you see the train is moving at velocity v. So if you are standing and if you see a guy on the train dropping a popcorn, whatever, so it will travel forward along with the train, and because of gravity it gets pulled down. So it is moving forward and down. It's basically a parabola. Okay. Now the question number 41 to team C. There is at the end slide, you can ignore it. The nature of charge of the particle is, there is a magnetic field going inside the board, and a charged particle is coming from A and going towards D. Who is saying the answer? I don't. Aman, did they say? That's wrong answer. So it is positive. So the last question goes to team D. What is the reason for the tides? I think similar question you had got. Yes, faster. It's exactly. It's just the gravitational pull. That's it. Okay, and that ends the quiz round. And by the time we extra question, we'll go to that video. we will watch that video done by NASA. So
near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation.
There's one more card.
Aditi is there. Okay, I know you might be tired, but this is the last one, and then you can move on to very nice snacks and tea. So this is Ask a Scientist. These are the 4 scientists from our institute. So that's Professor Sumati Surya from Theoretical Physics Department. Then Professor Pramod Pularkat from Soft Condensed Matter Physics Department. Then Professor Shiv Sethi from Astronomy and Astrophysics Department. And Professor Sadik Rangawala from Light and Matter Physics Department. So we have already collected your questions. And Aditi will be moderating. She has the questions with names and everything, and she will ask, and they will try to answer. Okay?
Hello? Okay, good. So I've organized the questions loosely based on themes. We can start with questions related to space and astronomy. I think this would be a popular question for all school kids. This was asked by Saugata from JTV Hebal, and they're asking, what is a black hole? Oh, it's KV. So sorry. The question is, what is a black hole? Is black hole and Big Bang theory related? I mean, are they related? Does time stop during traveling inside a black hole? What is a wormhole? When we travel through a wormhole, will we die? During traveling in a black hole, can we time travel? And there was another question related to black holes and wormholes. What is a wormhole, and is it true according to you? How do we come to know that there are more galaxies like Milky Way? So Shiv.
Okay, so I am Sumati Surya. I work in theoretical physics in the area of general relativity, where we talk about things like black holes, okay? So I think that one of the black hole questions is simply, what is a black hole?
Yeah, what is a black hole? What is a wormhole?
So black holes are basically, astrophysically, they're collapsed stars, and they're regions where if light goes in, it cannot come out. So light is trapped inside these regions. In the theory, Einstein's theory of gravity, basically what happens inside a black hole is there's some place where space-time becomes very, very attractive, or it starts to crush things together until you reach what's called a singularity. And that's where it's sort of similar to Big Bang physics, where you say, when you go back in time, you go back to a time when things are there's such a strong force, gravitational force on you, that you basically collapse and you get to the singularity. That's early back in time. So they're related in this way. Does that make sense to you? Does that make sense? Or do you have any questions about what I said? Because it may have sounded a bit more technical than you are used to. So imagine something that's pulling you really, like very strong gravity. So we know that on Earth we have a certain amount of gravity, right?
And if we went to Jupiter, would we have more or less gravity? More, right? So we'd feel the force of gravity a lot more, right? Even though we're the same mass, we'd feel the force of gravity. So in a black hole, yeah, go ahead.
Ma'am, will we feel the force from all directions only on one direction?
You feel it towards the center, just like we feel it towards the center of the Earth. Yes, so it'll be towards the center of the black hole. And what happens inside a black hole is basically that the way we think of space and time will change as you near this place, but we don't understand what physics goes on there, which is called a singularity. Okay, so it's something that we're all trying to understand what happens near a singularity. But it's basically, you can think of it as very, very, very strong gravitational force, which will basically, collapse us, make us very, we won't be able to retain the shape we're in and so on. So we can think of what they call tidal deformations that would happen inside the black hole as you're going towards the singularity. So somebody also asked, what is a wormhole, right? So wormhole, can I just quickly draw it on the board? It's just a very little, oh no, okay, so, okay.
We can
just
move it.
Okay, you can think of the wormhole like this. So say you have a door there, right? The door there, it opens out. And you walk out of there and you come out back here. Okay, that's kind of an example of a wormhole. It's connecting up parts of space, in this case just space, which you would think are very far apart, right? So wormhole, typically you can think of something where you're taking a handle of a cup or something and you're sticking it on this. That's how you would describe a wormhole. But you could also have a wormhole that goes from one time to another time. And then they talk about how you can build time machines with wormholes and things like this. I don't know if I answered all that.
Yeah. The student wanted to know if Big Bang and black hole are related and if time travel can happen.
I mean, time travel, I think Swati has already answered that question. Big Bang and black holes are not necessarily connected, but she did point out that there is a connection about singularity. The black hole is about a singularity at a point. Big Bang is a more complicated singularity, but yeah, it is some kind of a singularity, at least in classical general relativity. There was also a question about galaxies. How do we know there are galaxies outside?
Yeah.
What was the question? How do we know there are
How do we know there are other galaxies other than Milky Way?
So that's not an easy. So for that, you have to actually know. We have some idea of the lengths involved in Milky Way. We are around 8 kiloparsec from the center of galaxy. Kiloparsec, so 1 parsec is 3 light year. Light year, you know, right? You have some idea about what light year is. So 1 parsec is 3 light years. So we are from the center of our galaxy, we are around 8 kiloparsecs. So multiplied by 3, around 25 light years, 25,000 light years, right, from the center. So we have some idea how large our galaxy is. We can estimate distance to various objects around us. And from 1920s, people could do it and see that some of the objects are very, very far away, right? They are not part of our galaxy. The nearest galaxy is almost 700 kiloparsec. That is around 1 million light year away. So that's very far away. So that is how we know we can measure distances. We know the lengths in our galaxy. We know that we are roughly only 10 kiloparsec or 30,000 light year. That's how it is extent of our galaxy. But the nearest galaxy is very, very far away compared to the size of our galaxy, almost 1 million light year. And when we have found galaxies all the way to 1 billion light year right now, 1,000 times further than the nearest galaxy we have. So that is how. But how you actually find this distance is a very technical subject actually, so I'll not delve into it. But that is how we find it. So it's not easy. It was only done in 1920s. So it's a very good question. Because only in 1920s people knew that there was a world outside our own world. That means our own galaxy. It wasn't easy to do. It took a fair amount of effort. There were a lot of debates between astronomers whether what were called nebula are part of our galaxy or they're outside the galaxy. But now it's established they are outside the galaxy. So have I answered all the...
Yeah. Since you have the mic, Shiv, can you also answer a question like how can we count the number of stars in the Milky Way, and how many planets there are, and how our galaxy is formed in general.
Okay, how you find stars is the same way as you find galaxies. But the point is distances to stars is also difficult to find. But generally stars are point light, so they shine in a certain way, so we are able to figure out that they are a part of our galaxy, right? But again, it's not easy to tell a star from a galaxy when you're looking at very, very faint sources. But mostly we are able to tell. So just the way you found galaxies, you can find stars. So planets is a very difficult subject actually. You see how many planets there are out there is a very, very difficult question to answer. There was no extragalactic planet, extra solar planet known to us until 30, 40 years ago. Now, if I'm not mistaken, I don't know the exact number, you can find, there is a Kepler satellite which has found thousands of new planets around other star systems. Okay, I don't know the exact number is updated every day, I think, so you can actually take a look. Maybe that number is 7,000, 10,000, but how many are there is an impossible question to answer, right? Because there are close to 10 billion stars in our galaxy, right? Even more, 10 per 11, far, far more than that. But maybe 20% of star systems have planets, right? And they may have multiple planets, like Earth has multiple planets. It's a very difficult question to answer. What we can say is, so far, thousands of planets around solar like systems, planet systems, stars have been found, and they will continue to be found. Maybe some of you will grow up and find new techniques to detect planets. It's not easy to detect a planet outside again. So yes, so the whole point is one way to detect a planet. For instance, I'll give you one example. Like there are 2 or 3 very big techniques, but the simplest one is if a planet is going around the star, right, and you are looking along the plane. Okay, so what it do is planet will occult the star for a while. It block light, right? And that blocking of light would be a periodic signal, right? You see my point? The periodically it gets dimmed, then it lights up again. And the periodicity is related to the time period of planet around the star. This is just one technique, and this is not the best technique. The best technique is based on atomic physics actually. A certain line and its shift is measured. Best in the sense this technique only works if it is intercepted along your line of sight. Otherwise, you can't do that, right? The orbit is not like this, but like this, then you can't use this technique. So these are some of the techniques that are used to detect planets actually. And it's a very active area of research currently. And people like you will grow, you might develop new techniques, and you would know that so far, Earth-like planets are very difficult to detect for this reason also. Right? Because the whole point is they do not cause that shift, because they are not massive enough. Right? Jupiter-like planets, you see, if you look at the list of all the planets that have been detected, you will find more massive planets. You might wonder if it is a fair sample, it's not a fair sample. Right? You may have more Earth-like planets out there, which are very difficult to detect. So yeah, you can detect planets, and it's an ongoing area of research, very exciting area of research.
Thanks. And how are galaxies formed?
And how are galaxies formed? We do not have a clear answer to how galaxies form actually. We have a theory of how galaxies form. So galaxies are formed because of some conditions in early universe, and that leads to gravitational, so what you call gravitational instability. It's a bit like this. If you take a mass of gas and make one part of it more overdense as compared to other, right? That is unstable, that collapses onto itself. So I'll give you a simple example. If you take sun, for instance, you know sun is stable, right? It's stable for billions of years. But if you take out the energy, for instance, if it stops forming energy in the center, right? Then there is no pressure imbalance. So the whole point is there is only a gravitational infall. And it will take 5 minutes to fall to the center. If there's nothing else to prevent it, something else will prevent it. So this gravitational instability is responsible for formation of galaxies, but how exactly it forms is not known to us. Right? Exact mechanism is still a bit of a mystery. But there is sufficient evidence that gravitational instability of gas, almost near inhomogeneous gas, long ago, as starting from initial condition, that's how galaxies form.
Okay, thanks. In the next, I got a bunch of questions related to being a scientist and about scientific thought in general. So Abdul K has asked how to be a successful scientist. And on the same lines, a student has asked what was the key to success of C.V. Raman and what qualities as a student we need to apply from C.V. Raman's life.
So I'm Sadik. So the question was first, what are the, I mean, of course, if you ask different people, all of us will have slightly different variations on what it takes to be good at science. Okay, let's not say successful scientists or whatever, but what it takes to be good at science. And the most important thing is that you have to have the ability to question without, and question in a manner of, in a very ruthless manner. Till you do not have a satisfactory answer to your question, you keep asking the same question, maybe in different ways, maybe you try to answer that question. So the process is not just, it doesn't end at just asking the question. You should answer the question. Now, how do you answer the question? I mean, anybody can, you can say, why is the moon a ball of cheese? That's a question. But there's a method of answering that question which is contained in science. And science has a very constrained way of it prescribes certain method. Okay, it's called the scientific method, and this is based on logic, reasoning, and evidence. Okay, so you have to apply, so you work with a framework. You say, okay, I take all these things for granted because somebody else has checked all these things, and I have enough reason to believe that what is written in my book after that person has checked, it's all okay. So now you start in that, so that's one place you can start. And then you start asking your questions, okay, and you start getting answers. If your answers, so you can often start with a hypothesis, okay. You can say, all right, maybe if I have this mic and if I release it, will the mic go up or go down? The question depends on which way gravity is, okay. On Earth, it will tend to fall. But the point is that there could be some situation in which things may float up. So you have to ask the question in the context, and you have to have the ability to criticize. Remember, every generation of science grows on the back of previous generations, and often it is, while it is adding to the knowledge acquired in previous generation, it is also often in conflict. And the bigger discoveries in any generation are almost always in conflict with the understanding of previous generations. So the idea is that you should question, you should know what is the foundation. It is very important to know the foundation. If you want to do hard sciences like physics or something of that sort, then a mathematical ability, to cultivate a mathematical ability is extremely important, because mathematics is based on a logical premise, which is what science actually takes advantage of and builds forward. So, so sometimes you do not necessarily have a very clear understanding of where the physics is going to take you. But you can solve a certain situation mathematically, and you solve it for a certain, and you get a certain solution. Maybe you do not, when you did that solution for the first time, you do not necessarily understand what you are going to get. You do not even have a proper expectation. But once you arrive at that solution, you can then interpret that and then build your understanding backwards. Okay? And so it's a process. it's not like somebody just comes out of the blue and just, says, okay, I will see why the sky is blue and why the, why things fall to the earth. And, it's not like there is a whole bunch of questions. The most important thing in science, at least this is my experience, is to ask the right question. Often, when we ask questions, we are confused about the framing of the question. You frame your question properly, the chance that you will succeed at answering that question will increase dramatically. It requires a certain clarity of thought to ask questions with precision and in the framework. So you can always ask a question which is beyond science. Like right now, a question like what is consciousness is something which is right now beyond today's science. It may be something which tomorrow or whenever people may advance towards. But that is beyond science. So you can, that's too big a step. Okay? First, so you can start by understanding what your brain does. Okay? And then you have to understand what the cells do, how the nervous system works, how it all connects up. And you build like that. So, so this is, in some sense, what I've tried to do is to describe the process of science, of doing science. So you have to really keep an open mind. Everything can be challenged, but you have to challenge it right. You can't just challenge it because you don't like it. That will get you thrown out of the scientific seriousness circle very fast, because scientists do not want to abandon what they have accumulated over generations. Okay? And they are not fools. So you have to work very hard in order to make the change. This is very important. Okay? And so far as C.V. Raman goes, he was an exceptional person. He worked extremely hard. He was a civil servant. And after office hours and before office hours, he used to go to a scientific institute to do science. And this was when he was, I don't remember the position he held actually, but he was, I think, very high civil service position in Calcutta, where he negotiated with the local institute there, Cultivation of Science, which he used to pass, to actually do work. So, he not only did he work, do his day job, he did a night job. His night job was science. And this is what it took. But here is a remarkable person who had great acumen. He had a great feel for science. He had a certain way of thinking about nature. If you look at Raman's papers, what you will find that he has always taken his inspiration from his observations of nature. And there's a museum down this thing, I do not know whether you got a chance to see it. But you can see he has collected many things, and he has asked, why is the color of this thing this? And why is this shattering, why is this glass shattering from inside rather than from outside, and so on and so forth. So that's not the only way you do science, but this was how he did science. Okay? So he picked up from observations, he had questions, he questioned his surroundings, and he sought an explanation through precisely constructed experiments. And some of the instruments that he created in order to do this experiments were really works of genius. As instruments. Anyway, I think I'll stop here and somebody else can take it.
Another question this is open for all the panelists. Another question that students are interested in is, how do you actually become a scientist? What is the career path you need to take? What are the degrees you need to have?
Well, the typical path to become a scientist in our educational system is to, after you finish your 12th standard, then you choose science as your topic, which is like you go for a bachelor's degree, or in most places now you have a 4-year degree. which is a bachelor plus master degree. And after that, if you really want to practice science, then you do a PhD. Okay. Basically, PhD is that the process is that you join some lab or a group. Okay. So, and then you work with somebody or a group of people, and you learn the practice of science. Okay. That is when you actually start practicing science yourself. Okay. Till then, you are learning the foundations, you are learning various, like somebody said, mathematical tools which you may need, and the basic information and so on. But you have not had, you may have done some lab experiments, but these are mostly experiments where you're supposed to do something which somebody prescribes to you, and then you more or less know what result you are expected to get and so on. But once you go in for a PhD, you're working on your own problems. Some of the questions you may be asking here, and like Shiv said, some answers are not known, and you are seeking these answers. Okay? So the real practice of science begins from the time you start doing a PhD. There are exceptional cases where people have not gone along these paths and still have become successful and so on. But this is, by and large, this is the route. Was that it, or
Yeah, I think that
okay.
that helps. And yeah, I just want to add that a lot of institutes offer summer programs which offer students hands-on experience on different telescopes or experiments. So that is one thing that I wish I would have done when I was a bachelor student. Okay, moving on.
So one thing which a lot of you can do at home is, nowadays, because of internet and YouTube and all that, there are a lot of experiments and stuff you can do at home with things which are available in a kitchen, or simple things you can buy on Amazon and so on. So you people are at a big advantage that you can start playing with things much more easily than our generation could.
Okay, so the next set of questions are just general science questions. Renal wants to know, in the clouds, why do charges get separated? Is it because the positive charges are lighter and the negative charges are heavier?
You want me to answer?
Anyone?
So you see, this is electrostatics of atmosphere is not, it's not an entirely, again, it's not an entirely straightforward question, but one thing is definitely known, that this separation happens in clouds. But you see, there is always, when the air is lifted, there is a charge being deposited into the cloud also. So there is a cycle actually. When lightning strikes, charge comes down and then it gets lifted. In cloud, the charge separation partly happens for the reason what somebody said, that it's heavier. But sometimes it could be oppositely charged also. So we do not really know that much about how electrostatics in clouds happen. But it's a fact that the Earth cloud system, it's electromagnetically, there is roughly, if you actually see the potential difference between us, is around almost 200 volts. Of course, we are in equipotential surface, we don't get a shock because the whole point is we are standing on Earth, so it did not happen to us. But this is a very active system. During the day, the charges, like on a dry day, right, they get lifted and they get deposited. And at night time, light time, or generally when it rains, right, there is either a drift below, or generally lightning. I think, I don't remember the numbers actually, numbers I'm forgetting. How many lightnings happen each day on Earth this number is known. So we have a rough idea how much charge is brought back to Earth through the lightning. So it's a system, it's a cycle, and that's what you have to remember. I myself don't know more than that actually from what I have told you. Because from what I know, this mechanism is pretty complicated of separation of charges. Right? Because there is humidity and there is the water molecule, the way it gets polarized, and then it separates the charges. It's a complicated phenomenon, to the best of my understanding.
Thanks, Shiv. A couple of students have asked, how are magnets formed? How are magnets formed?
Okay, so if you, for instance, if the easiest way for you to make a magnet is to take a battery and and connect a loop of wire. Okay, if you just connect only a copper wire, you will short the battery and that's not going to be happy. So you put a little bit of resistance or whatever it is, okay, and you run a current through it. When you run a current through it, what is happening is that the charges are moving in one direction, okay, and therefore that creates a magnetic field which is going to circle around the lines of equal magnetic field, okay, are going to be circles around the tangent to the charge, to the motion of a charge at a point. Okay, and then you have to make all these surfaces, and you will get how the charge. This is the easiest way to make a magnet. But I suspect you are talking about ferromagnets. So now there is essentially three very kind of common classes of magnets which we know. I mean, there's paramagnet, there is diamagnet, and there is ferromagnet. So have you heard of Faraday's law? Right. So not everybody? Oh, okay. So it's a bit like this. So Faraday law, okay, then let me not couch it in terms of law. So if let's say I make these currents, okay, I create a magnetic field. So I can make a coil, okay, I can make a nice magnetic field, okay, in some direction. Now if I put some chunk which is not magnetic inside, what will happen is that this chunk has little atoms inside, okay. It is made out of, it has many other complications, but there is a crystal, the crystal is broken up, it is, there are little crystals which happen, but so there is a lot of complexity out there, but finally you can see that there is atoms. Now each of these atoms has electrons in it. So you can think of the nucleus as relatively stationary. It is not doing too much motion. Whatever motion is happening is back and forth, which is not necessarily doing too much for the magnetism. But if you look at the electrons, okay, the electrons are moving in some orbit, like planets in a solar system, and so they pose a magnetic moment. And so now what is happening is that you have put a overall magnetic field, and so now you have a little magnet in each of these atoms, and this magnet tends to follow the direction of this moment, of this field, and so that is your paramagnetic response, okay, to the atom. When you apply a field, you tend to put the magnet in that direction of the field. That is called paramagnetism. Diamagnetism tends to oppose the direction, okay. I'm just giving it to you. It's a little bit more involved to explain, but it's okay. And then ferromagnetism is something very peculiar. It happens because there are all these domain structures, etc., which you have in a magnet. So there are little crystals all over the place, and if you start with a ferromagnetic material and you do not put a magnetic field on it, then there will be no magnetism to that material. Now you put it in a magnetic field, it kind of starts aligning. But now because you have coerced it, you have actually pushed it, and it has permanently formed, because it is all these little things which are there tend to lock its ability to relax back into the old configuration. So when you subject it to a high enough field, you will magnetize it. So if you put iron in this current coil, you will magnetize it, and then if you want to demagnetize it, you have to put it in AC coil. If it's a DC coil, you will, but if you might have done this experiment, if you put it in AC current, then it basically, what it's doing is, it is putting the electrons this way, and then half a cycle is putting the electrons the other way, and so on and so forth. And then what you will do is, while this AC current is happening, you will dial down the current so that essentially it's going with lower and lower amplitude, and you will finally go through a cycle of demagnetization of this particular thing. The other way to demagnetize a permanent magnet like a ferromagnet is to heat it. If you heat it, it just, everything agitates, and then everything becomes more random, and that's how you, so these are some of the ways you, magnetism.
Right. Thank you so much, Adik. Sadly, we have to cut this short because it's 4:30. All the students are invited for cold drinks and some snacks downstairs. Thank you. Thank you, panelists.